Really? Doesn't have a spare USB port?
No, USB like this. It's like this one.
Yeah.
See. What? Huh? What do you want to plug in?
I was thinking I'll use my mouse to plug into yours. So we can.
Yes.
So
For people on the call, good morning, everyone. We'll get started in a couple of minutes. Okay. Good morning, everyone. Can people hear me on the call?
Yes.
Okay. Good morning, everyone. I think we have a growing list of attendees, and we wanted to welcome you to this tutorial on learn to drive and race scaled autonomous vehicles. This is an activity that is being delivered as part of the IEEE Smart Cities Week. And we have a wonderful program up ahead for you. The 4 hours will just rush by. And so before we get started on the actual tutorial, the Smart Cities organizers have asked us to highlight some details on the IEEE Smart Cities community and the ambassadors program. And so let me do that quickly. So I'll start by playing the video about the IEEE Smart Cities. For those who are not aware, IEEE is organized in the form of technical societies. And when there are new and emerging areas, multiple technical societies come together to form a community. And so IEEE Smart Cities community is one such. And I think the video will explain more details.
As cities grow, the pressure over the built space and environment increases, as well as the needs of the population. The complexity of the relations developed in the urban space also demands new forms of managing, planning, and living in the cities. IEEE Smart Cities brings together an array of technical societies and organizations to advance the state-of-art of smart cities technologies for the benefit of society by serving as a neutral source of information to industry, academic, and government stakeholders. The IEEE Smart Cities community is supported by 5 IEEE partner societies and 1 council, and they bring their expertise in the field to smart cities applications. We also have many educational activities within IEEE Smart Cities, including activities that count towards continuing education units. The most popular is the IEEE Smart Cities webinar, which counts with high-level technical specialists from many parts of the world, speaking about their findings on the latest trends, technologies, and solutions for smart cities. You can find the educational activities and publications in the IEEE Smart Cities Resource Center. In 2014, IEEE Smart Cities implemented a core and affiliated smart cities program in an effort to create a community to share best practices, discuss technical topics, and create a vibrant and worldwide grid of cities on the path to smartification. We also have 12 affiliated smart cities in 4 continents. And in the last 6 years, we have reunited our community at the core cities for the IEEE International Smart Cities Conference. This conference brings together practitioners, city policymakers and administrators, infrastructure operators, industry representatives, and researchers to present technologies and applications, share their experiences and points of view about current and future smart city applications. This year, the IEEE International Smart Cities Conference is going virtual. We look forward that you have the best experience wherever you are around the globe. We know that the pandemic restricted our opportunities to get together in person, in conferences and physical events, but we can still reunite through virtual conferences and webinars. To keep up to date with the IEEE Smart Cities community activities, join us in our social media channels on Twitter, Instagram, and LinkedIn. If you haven't joined the IEEE Smart Cities community yet, please access smartcities.ieee.org to learn how.
Okay, so I hope people got a flavor of the types of activities that the IEEE Smart Cities community is participating in. Within that, I think this year there was an innovative program called the Smart City Ambassadors. And one of the things that they wanted us to make sure everybody knew about was that you can be a Smart City Ambassador too. In this case, these ambassadors are responsible for helping organize events such as this one that we are part of. And it's aligned along the verticals of water, waste, transportation, healthcare, food, and energy. These ambassadors this year came together to create 30 technical events that are part of this Smart Cities Week program. And these are all, given the state of the pandemic, these are all virtual. And so the week started on Monday, March 21st, and we've had a number of these already complete at this point. But in almost all cases, the program is being recorded. So if you see something that's of interest to you, feel free to visit the smartcities.ieee.org website and then follow through on some of those links. So our program is now scheduled for the 10 a.m. to 2 p.m. today on Friday. There are a few other programs after today in the rest of the day today. But additionally, There are programs set up for tomorrow and some stragglers into the next week and next couple of weeks, actually. So by all means, feel free to explore. The last thing we wanted to highlight, last couple of things we wanted to highlight is that there's a Smart Cities conference and there's a call for special sessions and workshop proposals. That's April 15th. So you have about 2 weeks to do that. And additionally, and this conference is going to be in Cyprus. So always a good place to visit in the summer. Lastly, if people are interested in volunteering for the Smart Cities, on the website or on the smartcities.IEEE.org or on these sites, you have more details. So we are ready to transition into our tutorial portion of the program. We are a group of people that I'll introduce shortly who have been actively participating in what we call the F1 10th program. The F1 10th program was spawned at University of Pennsylvania. It was the brainchild of Dr. Mangharam, Dr. Behl, and Dr. Abbas. And a group of us have then come together as part of the extended program. And today it's our great pleasure to be able to highlight to you some of the innovations that have happened here, as well as to allow you to come up to speed with racing, both virtually and with your own physical F1 10th vehicle. So stay tuned. But first, I wanted to introduce all the people who were involved in today's delivery of this tutorial. There's Dr. Mangharam, Dr. Betz from University of Pennsylvania. Dr. Behl from University of Virginia will be joining us shortly. There's Dr. Abbas from Oregon State and Khushal, Brahmbhatt. And from Clemson, Ajinkya, Joglekar, Ameya, Salvi, Adhiti, and I round off this complement. So we have, what I'd like to do is invite Dr. Mangharam to now quickly introduce himself. And in order, just before we do that too, here is the rough agenda for the day. We're just past the introduction and welcome note. And as we will dive into the program, it's set up in these segments that each one of the leads are noted here. So we'll start off with an overview of autonomous driving, followed by follow the gap topic. There's pure pursuit. There's graph-based planning for Raceline optimization, and ending it with multi-vehicle racing. So to quickly introduce the speakers for each section, let me welcome Dr. Mangharam.
Hi, everyone. We are super excited to talk to you about, how we can bring to you, this autonomous racing as a very efficient way to learn about, the whole pipeline about perception, planning, and control for autonomous vehicles. My research interests in autonomous vehicles have been, for the last 20 years, and I focus on building safe and agile autonomous systems, whether they are implanted in the body as medical devices or autonomous vehicles or energy efficient building automation. We're very happy to have you all here, and we hope to have a great session today. Thank you.
Next, I'll introduce Dr. Johannes Betz.
Hi, everybody, and welcome to our IEEE Smart Cities workshop today. So everybody's probably asking themselves, like, why should we do autonomous racing? And I can give you a short answer: because you can have an awesome career with it. Because I'm the best example, because in the last couple of years, I focused on autonomous racing vehicles because it is an edge case and it shows us how, or demonstrates us how to operate vehicles on the edge, high speeds, high accelerations. We can learn a lot from them, and therefore my research expertise is in the field of autonomous vehicles with a focus on SAE level 5, advanced machine learning technologies, path and behavioral planning. And that's why I will show you today one of my research expertise, the graph-based planner. I'm happy that everybody's here and looking forward to talk to you.
Thank you, Johannes. Next, I'll introduce Dr. Behl briefly. He will introduce himself at the point when he comes and presents in his session. But Dr. Behl graduated from the University of Pennsylvania and is an assistant professor at the University of Virginia, where he's part of the Cyber-Physical Systems Link Lab. And as part of this, he's participated in a number of mission-critical cyber-physical system research. But the most prominent amongst these is, of course, both the F-110th and the full-scale autonomous racing that he's done, where this vehicle now raced at the Indianapolis Motor Speedway and at Las Vegas. But stay tuned, he'll tell you all about it himself. Next, I'll introduce Dr. Houssam Abbas.
Good morning, afternoon, and evening, everybody, wherever you may be. So I'm Houssam, and when we talk about autonomous racing, it's very exciting, but what really gets me going is finding the areas where these systems can fail so that we can then improve them. So my research expertise is in applied formal methods, and my goal is to develop verified and ethical embodied autonomous systems. And the typical application areas are in unpiloted aerial vehicles, self-driving cars, but also large-scale sensing, where we think about how we can use these autonomous systems that have to live together and cohabitate as sensors and as actuators. Thank you.
Great. Thank you, Houssam. Next, Khushal Brahmbhatt.
Yeah, hey everyone, I'm Khushal. I'm a graduate student at Oregon State. My research mainly focuses on multi-agent systems and motion planning in autonomous vehicles and UAVs and drones. So I've worked previously with a lot of deep learning methods for motion prediction and planning, and my current research focuses on studying fairness in motion planning using formal methods and mixed integer optimization.
Thank you, Khushal. Next, I'll invite Ajinkya.
Hey, everybody. My name is Ajinkya, and I'm a PhD candidate here at Clemson University at Automotive Engineering Department. And my research domain is pertaining to robotic hardware and software-based deployment, mainly focused on scale vehicles. And this is done in context of research as well as in an education setting. And the application areas I'm focusing on is hierarchical motion planning and path and trajectory tracking, along with reinforcement learning for autonomous navigation, going from real to sim, training it for optimal policies, and then doing a sim to real to put it back on the real hardware.
Thank you, Ajinkya. Next, Ameya.
Hello all, I am Ameya. Similar to Ajinkya, even my research areas are mostly in data-driven controls, machine learning-based deployments, and mostly working on scaled vehicles for simulation to reality transfer. Even I am a PhD student at Clemson University, and I hope you all enjoy this session. Thank you.
Thank you. Next, Adhiti.
Hi, I am Adhiti. I'm also a PhD candidate at Clemson University in the same automotive engineering department. I was part of some of the initial development of the scaled AV research at our university several years ago. But since then, my research area has progressed from scaled AV research to cable-driven robotics, employing a lot of the same theory that we use in mobile-driven robots, but in a completely different application area. So that is a slight difference, shift in focus.
Thank you, Adhiti. And lastly, I just wanted to quickly introduce myself and how we got engaged with the F-110th program. So I moved to Clemson in 2016 fall, and as I was looking to develop a new course in robotics, I had a chance to speak with Rahul. At that time, Penn was starting to roll out the F110th program, both internally within Penn, and they were inviting partners to join. And so in January of 2017, we deployed the first class outside of Penn with the F110th program, I believe. And at that point in time, Adhiti was the TA for the course. And since then, she's helped to deploy this with other industrial partners and so on. But our overall research, just a couple of words about myself, I'm looking at what are called connected autonomy systems that blend autonomous systems, sense, think, and act in real time with this notion of connectivity, and to be able to then deploy this in a range of application arenas. So there's the on-road application that I think everybody is familiar with in the context of self-driving cars. But there's a big future in some of these non-traditional platforms, two-wheel platforms, such as the ones that you see there. There is an entire off-road arena that started with space robotics and is now growing into precision agriculture and other areas like that. And last but not least, it's the manufacturing shop floor. So our students have found that the same technologies and the technology base with the F110th program has proven very useful for them to branch off into a whole host of other arenas. So with that, we'll come to the end of this first part, the introduction part, and I'll next ask Dr. Mangharam. I'll stop sharing my screen and I'll invite Dr. Mangharam to share his screen.
Sure. All right, everyone. So it's great to kick off this session. Let me know if you can see the screen well.
Yes.
All right, great. So we started this journey on autonomous driving several years ago, and then we realized that civilian autonomous driving has a wide range of driving scenarios and a wide range of as Johannes mentioned, edge cases, which are really like these cases that are not easy to find in terms of high risk, but maybe low frequency, high severity cases. And that's when we said, well, why don't we just focus only on extreme driving and driving at the limits of perception, planning, and control. And that's when we started to look at autonomous racing. And so by way of introduction, my research career is focused on generally in this area of real-time systems and cyber-physical systems focused on life-critical and safety-critical applications within, say, the human body, like implantable medical devices, ensuring that the interaction between the device and the physiological system is safe. And similarly, we use the same techniques of formal methods, control systems, and data-driven kind of machine learning approaches for building, and evaluating and verifying the safety of systems, whether they are autonomous systems in vehicles, in buildings, in industrial control. So I'm generally interested in these aspects of, this question of how do we provide safety and performance guarantees for closed loop life critical systems. And so as part of this effort of building, a very open source environment for where students, faculty, researchers can come together to build, these autonomous vehicles at a low cost, at low risk, where you are fully involved in the development We have a large team of people, and this list keeps growing on, who have contributed to this work, and we are very grateful for learning from each other, because there are several topics involved. And what we aim to get for you today is a very efficient manner of getting a quick overview of what are all the key components involved in driving autonomous vehicles, and looking at it from the perspective of racing. And I'll shortly explain why we care so much about racing as a method of education, as a method for learning about these autonomous systems where the decisions are being made on our behalf, maybe with or without our consent, and there is a risk of life involved in this. So as part of this, we'll divide the lesson plan for today into two parts. One is, let's just learn to drive. Let's understand what are the basic building blocks of perception, planning, control, so that we can actually get a car to drive, to navigate efficiently, and to avoid crashes, and so on, to use the inputs from all the sensors and connect this sense, plan, act, closed loop system. And I'll also introduce this F110th platform. This is just one of many platforms that are out there, but it's a very low cost approach where any student can actually get involved and actually have a hands-on manner in designing, deploying, verifying, and evaluating algorithms for autonomous driving. In the second part, we will sort of look at how to race. But for going back to the first part, we'll look at these reactive algorithms. That means without any map, I'm just using the streaming inputs of my sensors. How can I actually avoid obstacles? How can I navigate efficiently? Then as I start to build a map and start to get more information about my environment and what is around me, then I can start to have more optimized paths along which I want to race. And the difference between civilian driving and racing is that if I were to drive, say, from Philadelphia to New York City, and I reach 5-10 minutes late, people are like, okay, that's fine, at least you're alive. They don't even say that, but essentially having a little bit of delay is okay. But in Formula One racing, for example, being even half a second too slow for a lap means that you're out of the top 10, right? So essentially with racing, we get a very good idea of how do we balance safety and performance, and we'll talk more about that trade-off over there. And then as we get to now learning to race, we have to now come up with much more, from simple ways to follow a path, to then coming up with planning approaches and global planning approaches to find optimal race lines, to local planning approaches and tracking approaches using model predictive control to efficiently navigate through the course and to overtake opponents. And so essentially we are in a very adversarial environment. So let's start with how can we learn to drive, and I'll give you an overview first generally of what is involved in autonomous driving. Many of you all will have good ideas, but we're just sort of setting the field over here very briefly before we dive into how we actually go about teaching this in much more detail. So there are unicorns outside today that are these companies that are funded several billions of dollars, and what they have done now is they have come up with many different ways in building autonomous vehicles. So the Tesla system, for example, just has a lot of cameras, right? It's a fully camera-based solution. They want to, stitch together the 360-degree view and have situational awareness, but through monocular cameras, and extract depth, extract situational awareness, and then do their planning and control based on those inputs over here, right? So, and they have decided that that's the way they will go. It's similar on a different level. Waymo from Google has a mix of radars, lidars, cameras, and a lot of sensors involved over here. A lot of redundancy. They're taking a much more diversity in sort of sensors that they have to extract depth, to get much more about the semantics understanding of the environment, And they have both, what the systems are running online and versus all these companies have a lot of training that is being done offline, right? Based on all the collected miles that they have. Uber, for example, again has a mix of cameras and lidars. Just to give you an example, these are mostly like retrofitted on existing gasoline-based vehicles. And the future is really going to a very different kind of platform where we have electric vehicles based on skateboard chassis, which are going to be very standardized. And then the autonomy aspect will be much more simpler, much more efficient, because you're working off very standardized chassis. You don't have to retrofit these legacy vehicles. And so you can think of this as autonomous vehicles 1.0 is, let's invest heavily in building maps and HD maps, and invest heavily in actually rolling out these vehicles and getting a lot of miles under the hood. And then autonomous vehicles 2.0 are on more efficient electric vehicle platforms, standardized chassis, and they are going to be much more reliant on learning-based approaches, which are like these end-to-end learning-based approaches. And as we'll see towards the end, that these provide a lot of unknown and high risk, and that's sort of one of the challenges. So we like to think of autonomous vehicles and then specifically autonomous racing as literally and metaphorically a vehicle for learning about these safety critical environments and safety critical systems. And so we are not necessarily only focusing on vehicles, but it's today's sort of model, today's system to understand what future autonomous vehicle challenges, autonomous system challenges we'll have. So let's take a look at from the perception side on the left. The system is capturing many different views of the world. There's a RGB view right on the top from the cameras. Then you see in the black and white, there's the depth view of how far objects are. There's an optical flow view of how fast objects are moving around you. So you can actually focus on objects that are coming in very fast and very close. And then we do like through the pipeline, object detection, object tracking. And finally, at the bottom, you see there's semantic segmentation, which is really telling you what's a drivable surface, what are different types of objects, and helping you then plan through that. So all of that is fed into the sensors and perception block. And that then feeds into the planners. And essentially, we're going to go through this loop of sense, plan, and then act, and do this loop about, say, 20 to 100 times, a minute through, so that we can keep updating the system over here. So as we plan now, the mission planner is like Google Maps. It's saying, okay, I want to go from Philadelphia to Times Square in Manhattan, and says, well, take this path, get onto the highway I-95, and then drive for 100 minutes along that way. The behavioral planner then says, okay, in order for me to get to the highway, I need to take this on-ramp. I need to switch to the left lane. I need to overtake this vehicle. And so it's making these discrete choices based on the local environment. And it's very different from like a mission planner, which is really just looking at the global view of over several minutes. The behavioral planner is looking at in the tens of seconds. And then the local planner says, okay, well, the behavioral planner has told me switch lanes, get onto the on-ramp to get onto the interstate. So the local planner has to figure out what are feasible paths in the near term, say within the next 1 to 10 seconds. How do I now, what is my way to go from this current position to the next position? And has to figure out feasible pathways and then pick among those feasible paths, the most efficient paths and safest paths to go forward. And that then feeds into the input to the actuators to generate sequence of steering and acceleration inputs. And then this process keeps repeating. And we are essentially having a very tight loop over here where there is a lot of compute intensive work happening on the sensors and the perception side. The planner is looking at multiple time scales of planning. And then the actuation is happening, several times a second, and the vehicle is correcting its course accordingly. And we want to make sure that this is all safe, right? So since these vehicles have come to the road, you can see here there's a autonomous vehicle driving on the road, and there's a minivan parked on the side. And while this car in front just moves aside, this autonomous vehicle doesn't see this truck literally and taps into it. So that's not a big deal. It's a mild tap, and this is back in 2016, so quite an early days. Then again, later in 2016, there's a higher speed drive of a Tesla driving on the road, and it sees the we can see the street sweeper on the left-hand side now. The vehicle just basically goes and crashes into it, and a 23-year-old male dies on the spot. And so this is something that, as drivers, we would have seen it and avoided it. Again, this is not anything against Tesla specifically. It's really, they are the only videos that we get are from these Tesla vehicles on the road. But this is one of many examples of, things to come actually. And whether this method of evaluation is right or not, right? So similarly, in 2018, we see more and more of these cases, vehicles taking a sharp turn along a cliff, and then it crashes onto the side. And so these continue to go on. It doesn't mean that, these cases are, the predominant cases, but however rare they are, we need to understand the underpinnings of, why these cases are happening, and how do we actually, understand the underlying engineering causes for this, right? So, and that's our focus, because even as recent as last summer, more than, almost 300,000 of Tesla vehicles were recalled because of safety concerns and due to the autopilot system. And this is not just Tesla's issue, it's all the, companies or all the production systems that are going to come onto the road, and how do you evaluate these, right? So, so that brings us to our main question for today's session is, we are always trying to balance between performance and safety. If you look at this vehicle over here on the right-hand side in this box, it's trying to merge onto that on-ramp on the highway, and it's trying to see whether this, this truck over here will give it some space. And if it is, you want to try to have a merge without much hesitation, without much delay, and have a smooth merge. And if you stop on the road, that's a risky thing, right? So, but if you're too aggressive, then you can cause the problem. You can actually cause a crash. And so now we want to take that to the extreme. And here, if you look at this Formula race over here, I think there's Alonso and Vettel over here driving at, over 200 kilometers per hour, and neck to neck, high speed, very expensive vehicles. They don't know what each other are going to do next, and but they have to race to win. And so this is really pushing us to the limits of, not just as we see on the road, a mix of cooperative and, aggressive drivers. This is on the extreme of adversarial drivers. Everybody is against you, and you got to figure out how to overtake them and win. You have to figure out how to get the fastest lap time. And you can't, if you're too conservative, you lose. If you're too aggressive, you crash. And both ways, you don't win. So how do you balance that dynamically based on the driving context and be able to win at the same time, right? And that's sort of why we would like to focus on racing over here. And so the course is known, and we're really focusing on just this scenario itself, right? And whatever we can learn from here, we can take that forward to autonomous vehicles. So here we are driving at, we need to detect the vehicle's limits, because we can't push it beyond that, but we want to operate as close to the vehicle's limits. We have very unstructured environment, and you can have different track conditions. So you can't just mine data from the past, because every driver is going to have a different strategy for the next day. And so this is a very small data regime over here. You have very high prediction uncertainty based on how other drivers are going to drive. And then you have to figure out what kind of racing strategy to have and how to make these decisions in a very short time, right? And then you're driving this vehicle at the handling limits over here, very high speeds, high accelerations, and a lot of compute requirements for autonomous racing systems. And you have very short reaction times to do this, right? So we are really literally at the driving at the limits of perception, planning, and control when we move this racing context to autonomous racing. And by working in that, that corner of this, of the operating regime, we're able to expose the system to a lot of high risk scenarios. And that's where we want to focus on. So F1/10 is one example of 1/10 scale autonomous racing cars. And so it's 1/10 the scale, but we like to think of it as 10 times the fun because you get to actually build everything, right? It has a good base of open source software, but you can do everything, and we'll walk into that in more detail. There have been an explosion of different racing competitions like Robo Race that Johannes will cover later on, and the India Autonomous Challenge that Johannes and Madhur will cover later on. These are real full-size racing cars costing over $350,000 with full-blown sensor pipelines and running Linux-based software and making these decisions on the fly. And then there are Formula student groups are all moving from electric to autonomous electric systems. And so this is a very you can kind of graduate from the scaled environments to the real system. And our goal is to say, let's learn everything at this small scale environment, and then you're fit enough as an engineer to apply it at the full scale. And essentially, we're going to walk you through this sequence of let's understand what sensors are involved, what kind of inputs they have into the perception system, how do you do localization, how do you do object detection, and then we go to planning for prediction based planning, behavioral planning, and then generating trajectories to avoid obstacles and to get on to the optimal pathways so you can actually achieve the highest speed across the lap. And then in order to execute that, you need to figure out what's the near-term pathway, and how do you manage, both the direction, the steering angles and the velocity of the vehicles. And you want to put all of that to run on this race car, right? So this is quite a bit of things that are involved over here. And each one of us is going to walk you through that. I'm going to walk you through how we designed this as a course and as a way to explain to you the different parts in the next 10 to 15 minutes. So essentially, these all the work that we do is built on these 1/10 scale autonomous racing cars. They come with LiDARs, RGB cameras. They have a onboard GPU system, the Jetson, and now we have gone from the TX2s to the Jetson Xavier NXs, very powerful compute systems that natively run, machine learning based pipelines and classic computer vision pipelines. And so we've taken care of all the things that you don't have to worry about now. The car is ready. And if any people are interested, you can get this from the f110th.org website. And it's free, it's open source, and we'd be happy to help anyone get started. Also, the website has courses, ways to learn to build and drive and race these systems, all IKEA style instructions on how to build the systems, lecture material, labs on how to get started. And so I'm going to give you a glimpse of how we do that, right? So we built this reference model of the car, and everyone can then use that reference because, the hardware has come together, many sensors are put together and integrated in the system. There is a very good autonomous vehicle software stack that covers perception, planning, and control, all runs, on the onboard NVIDIA system on CPUs and GPUs efficiently. And you can use all the algorithms that we talk about today out of the box, right, in this system. So you don't have to worry about making a new system or another car. This car is ready. Now let's focus on algorithmic development. And that's allowed a lot of research in the IEEE smart cities communities and in robotics communities and so on, to work on safe autonomous systems, secure autonomous systems, multi-vehicle coordinated autonomy, and looking at energy efficient, time efficient algorithms. And this is all supported through different algorithms and simulation environments that we'll talk through. And our goal for today is, and through the course that we teach and through the community of F110 community, is to help students, faculty, researchers, hobbyists build, code, and race these systems. And so you have a bunch of parts, you put them together in less than 1 to 2 hours, and then you have your vehicle, it's done. The rest of the lectures over here are not about how to build your car. That's pretty straightforward. We've done the, let's say, all the groundwork for you, and now you have a car. It's ready to code, and you can directly code on the car itself, right? The car is running full-blown Linux, and essentially you can just SSH to it, or a remote desktop to that car, and now you can run your code directly on that. You're not running your code on the laptop and transferring it to the car. You're just actually coding and doing everything on the vehicle. And as part of that, we developed a course schedule, and we offer this course, many years. It's also fully online, and all the lectures, videos, labs, everything are published on the F110th website. And so essentially this course is broken into, 6 different modules and we'll walk through each of these modules, but taking every student from scratch. We don't assume too much in terms of what background knowledge they have, basically just linear systems, basic probability, and basic coding in Python or C++, but nothing beyond that, because this is really bringing together all these aspects of, first we start with the software system and robot operating system, introduce the vehicle, introduce the simulator. Then we move on to reactive methods, which are basically just saying, I'm not going to build a map. I don't know much about my environment. I just know what I can see right now, and how am I going to navigate through that world. Then we go into mapping and localization, where you understand the basics of simultaneous localization mapping, the math behind it, the software, the code behind it, the algorithms behind it. And then how do you actually build a map, localize yourself, and once you have localized yourself, how do you plan a path around it? What are simple ways to plan the path? What are more efficient and sophisticated ways to plan around that? Then we have components on learning and a learning-based computer vision, classic computer vision, and more special topics. The nice part about this course is that it has no exams and no midterms. It just has 3 races. After 6 weeks, there's race 1. After the 10th week, there's race 2, and then it ends with a final race. Each race is really building on the course material, and there are 8 labs involved in this course. And the labs essentially help the students build competency in each of these, and you then deploy them in the race. And since it's a friendly competition environment, it really it's a lot of fun, and it really gets the best out of all the teams over here. So in terms of AV driving basics, we'll start with the basics of automatic emergency braking. How do you build a car to actually be safe, right? You don't want it to crash. So how can it sense, obstacles? How can it actually stop and do automatic emergency braking before it actually hits the obstacle, right? So you understand concepts about, time to collision, how to interface the LiDAR sensors, how to understand failure modes, what are serious problems in terms of, false positives, but more importantly in false negatives, and actually detecting that through the LiDAR data that you're getting and being able to close that loop. So that's essentially just the first 2 weeks. You understand ROS, then you deploy the safe thing. You will also use the F110 simulation environments. They're both in, OpenAI kind of gym interfaced gym environments. And we have all of this on our F110th website on GitHub. And then there are, also fancier simulation environments like the LGSVL that have our F110th race tracks and race cars involved for more perception-oriented research and development over here. The nice part is that this environment makes it very convenient for development. And so you would spend about 80% of the time developing rapidly in this environment. You can crash quickly, you can recover, and then you move whatever code you have running in these environments here, they directly work on the vehicle, and then you adjust for reality, right? So there is a simulation and reality, and then we are bridging the sim to real gap. And So you understand, how sensors are placed. That's lidars, cameras, and the basics of kinematics and mechanical engineering in terms of pose representations and transforms, rigid body transforms. How do you understand the sensor's view of the world and translate that to the vehicle's view, to the global map view, and whatever you see you have problems in terms of doing coordinate transforms and pose representations in the real vehicle, because you have multiple sensors and each sensor is viewing the world from its own frame of reference. And how do you combine that to have to map it into a global reference? We have to do the same thing on our vehicle over here to capture these multiple sensor views. And essentially, as you can see over here, we have a local frame of reference, which is where the world is moving around us and we are sort of fixed, versus you have on the left side, and then you have a global frame of reference. And how do you translate to that, right, where it's much more easier to understand where you are on a map and combining all the sensor views. Then you work with the actual vehicle and tune the speed controller and the steering controller, which is again a easy to access system. It's all in software now. You don't need to do any soldering or any hardware development, and you're just tuning the system over here to understand that. Because then you need to understand reactive methods. I'm getting my sensor inputs and I need to do rapid obstacle avoidance. How do I do that? So first we have wall following, where you just detect the wall. It's kind of like you would have in high school or middle school, and then in undergrad courses where you're doing a line following. But here we are following the wall using the LiDAR. And you can see the vehicle is able to navigate. It's doing it rather slowly. And this was how some of the early races we had in 2016, 2017 did that. Just reactive methods for that, right? So then you understand how to tune your PID controller. And there's a lot of work done, by Houssam, who will talk about now how do we go from single car to multiple cars later on. But this essentially helps us now in terms of tuning to know how do you have how do you tune your PID controller to have very smooth navigation and to follow a path without much oscillation over here, right? So once you have your car, that's tuned and ready to roll, you then program it to do obstacle avoidance. First, you do that, for the map, for the real world map, but in simulation. And once you're able to navigate that very efficiently, then you put the vehicle actually in the real world and you can see it work in action like that. So the simulation environment helps it reduce a lot of frustration also, right? So, and then moving forward, with the first race is just using these reactive methods. Here's an example of a race we had back in 2018 in Portugal, and where you can see the cars are going around the track, but just using the LiDAR inputs streaming in. Right? It does not have a sense of a global map. It's still able to do pretty well. Then moving forward, we have map-based methods. And so essentially here, we have to understand the basics of scan matching, which is an integral part of the SLAM algorithms, of simultaneous localization algorithms. And we understand one particular method called iterative closest point algorithm. That's basically saying that if I have a previous scan and then I take a new scan, how do I try to match these scans to know essentially how the robot has moved from the previous frame to the current frame? And so what are efficient ways to do this? How can you do this in real time? And so essentially we read a paper that implements this, scan matching algorithm, and that allows us to then code it up and really get a very in-depth look at, what's involved under the hood with these SLAM algorithms. Then we use, off-the-shelf SLAM algorithms. These are running on the car to actually then build a map, and that once we have a map of the racetrack, then we can actually drive through that environment. So essentially, as the car is driving through this environment, we have a very high quality map, and this runs very efficiently on the platform. And then now you're using this map. Now that you have a map, you need to localize yourself. And so you also understand and code particle filter based approaches to make guesses as to where you think you are, and then use this kind of recursive Bayes filter approach to then efficiently localize yourself and get high accuracy in terms of your pose, your direction, and your position in the global map. So now that you have a map and you can localize yourself, the next step is to say, okay, I want to now drive along a certain path. So then you use this approach called pure pursuit to actually chart out a reference trajectory and then to follow that trajectory very efficiently. So this is kind of like your first racing path that you say, okay, you know the global map, now race along this as fast as you can, determine the speeds along each segment over here, and how you're going to smoothly turn along that, right? And essentially now you can see that once you're able to do that, you can drive the car much faster. And here you can see our teaching assistant who is getting a good workout, but essentially now this car is driving, twice the speed of the previous reactive methods over here, right? So we are getting much better. The car is getting much smarter, much more aware. And then that takes us to the next race, where you use these map-based methods to efficiently navigate through the track, and you can figure out, what is the most efficient pure pursuit path to use. And this is the next year of our competition race in 2019 in Montreal, where most of the teams used this approach. So we use these competitions as a way to even, further how we teach the course also. Whatever was done in the competitions is pushing the limits, and then that allows us to incorporate a lot of that in the course. That brings us to the final part of motion planning, that, how do we have more efficient methods of motion planning, more agile methods using, say, rapidly exploding random trees, and variants of different, motion planning methods that you can then do both in simulation and then you can actually execute that on the real car. And in order to then do the tracking of the vehicle along a motion path, we introduce model predictive control as the next step up from PID control, to then actually have a combination of safe and efficient pathways for the vehicle to follow and to do that smoothly along the track. And then finally, we introduce different concepts in learning and vision. We start with, classic computer vision, that's saying, okay, how do you detect April tags? How do you estimate the distance of vehicles around you? So single view geometry, homography, detecting features, and prediction. And then that allows us to, then we also have a lab on how to train, based on a data set of vehicle images, to then identify the vehicle without, these April tags, and to develop a convolutional neural network based object detectors to then use that as for overtaking that, right? So essentially this is like lab 7 out of 8 labs in the course, and students develop this, detection pipeline and have to make it run fast, right? So in this case, in this video, this pipeline was running at about 72 frames per second on the platform. And that then introduces us to a lot of projects that the students then do, say like this is, imitation learning, where you drive the car for 5 minutes and then, the system learns to drive, as well or as poorly as you. And you can see it's trying to minimize the error in how you would have driven versus how it starts to imitate how you drove, right? So this is one way of training, and this was used as a reinforcement learning based project as an option. And finally, we get to the final Grand Prix, where students are taking in all of the stuff that they have learned in these 8 labs and putting them into action over here, where it's head-to-head racing, 2 vehicles driving against each other. You've got to detect the other vehicle and figure out how to overtake them. Both are trying to, aggressively win the race over here. And so this is, again, in one of the racing competitions that we had pre-COVID. And that's, that brings together perception, planning, and control, and you're ready to race at this point. So I'll be happy to take any brief questions, or, or we can continue on to the next, right? So, or any quick questions that are there, right? So, and any people who have any questions, you can also check out F1 tenth.org, and that has a lot of details there. And yeah.
Thank you very much, Rahul, for a phenomenal presentation. I think there were a few questions that were put into the chat. We'd invited people to put their questions into the question and answer box or chat. And there are some logistics ones, such as, will the video be available? And the answer is yes, on YouTube soon. And the presentation PDFs will also be made available. We've also included in the chat links to the F110th webpage, the LinkedIn page, the Twitter hashtag, the Facebook hashtag, GitHub. So the F110th maintains a very robust GitHub page with lots of up-to-date material. So even as you go to the F110th website and work your way through the build and then the learn, there's lots of supporting material, code base that people have used to then come up to speed. So at this point, we are ready to transition. And I'd like to now invite, let me share my screen once again. We are going to have two sessions back to back. One is Follow the Gap, and the other is Pure Pursuit. The Follow the Gap session is going to be introduced by Ajinkya Joglekar, Ameya, Salvi, and Adhiti Raman from Clemson. And so without too much further ado, please take it away.
All right. Is the screen visible to everyone?
Yes.
Yes.
Perfect. So Adhiti will be kicking off this section. So,
Hello. Can you hear me? Am I audible?
Yes.
All right, thank you. So we'll be starting the session off first with a discussion about reactive planners. And it'll be introduced by me, by Ajinkya, Ameya, and myself will be participating in the discussion of this particular section. So when you have a course such as this with a number of obstacles in it, what is the best way in order to navigate a course like this? Are there any suggestions from the audience? If not, I should just go ahead and talk about some of the different ways in which navigation of such a course can be addressed. You can have a map, for example, like a hectare map or some sort of occupancy grid map of this entire area, create a race line like Dr. Mangharam has mentioned multiple times, and then have a planner in order to move the vehicle around that race line. But another way to approach such a map is to have a reactive planner, that is without any foreknowledge of where the course is, how the course is shaped, where the obstacles are. A better way to, or a different way to approach such this thing is to have a reactive planner that is only locally reacting to the obstacles and the environment around the vehicle. So how do we best develop an obstacle like that? What are the objectives that we want from something like this? We want to essentially be able to keep away from the walls, at the same time avoid obstacles that are both sparse and cluttered. Not. As you can see in this video, this vehicle is using a reactive planner in order to navigate this. Sorry?
okay.
Yeah, this is, as you can see in this video, this vehicle is reacting to a follow the gap algorithm. And you can see it's a reactive planner, especially because the PID is not particularly tuned well in video. You can see the certain oscillation as it comes to a smooth walled environment. But the advantages of having a reactive planner such as this is they can be quite agile and very responsive to both cluttered static obstacles as well as dynamic obstacles. In this video, this is a video that Dr. Mangharam students have taken during their F1 10th competition in 2017. It's a few years old, but this shows a very effective demonstration of a reactive controller around a track that is free of obstacles. You can see that it's not necessarily, the vehicle is not necessarily keeping to the center line of the track. It is going fast during straights and slowing down over corners in order to take these turns effectively. And it is also a little bit free of the kind of oscillation we saw in the previous video, which shows a very well-tuned controller or certain modifications on a very simple PID controller. So how do you get to that kind of a performance level? How do you get to that kind of performance without a map, without having a defined race line? You can have one of the more basic controllers is the follow the gap controller, and certain extensions on the reactive, on certain extensions on a very basic follow the gap controller can lead to very good performance from this controller. Ajinkya and Ameya will discuss the disparity extender and other approaches such as the bug algorithm later on in this lecture. So given that you have a scan of the area, given that you have a LiDAR on the car and you're getting a LiDAR scan of the environment, how do you define the most optimum area that the vehicle should traverse? You can see that all of these red lines, all of these red dots, each represent one laser interference with an obstacle, and the y-axis shows the distance of that interference. So, for example, you can see according to this figure that there are some obstacles here that are close to the vehicle, such as these are very, very close to the car, whereas these are somewhat close to the car. But on the other hand, these obstacles here and here, these obstacles are quite far away from the car. They are at a good amount of distance. So if I wanted my vehicle to travel forward, which is the most preferable area that I would want to travel in? It would be closer towards either one of these obstacles, right? Because I want to avoid all of the close obstacles. I would want to either go towards this or I would want to go towards this and then plan the next direction again. So reducing that problem to a smaller toy problem, where would you expect the vehicle to travel? It could travel, given that you have a list of 12 LiDAR points here, you would think that because this point and this point represent infinity, which is that a LiDAR scan has gone through this point but never come back. It means that these areas are completely free of obstacles. So ideally, we would want to travel through either this particular point or this particular point. However, as you can see that in this particular area, these are two obstacles that are very close to the car beside this area. So even if we move in this direction, the car will not be able to traverse through this gap because the width of the car may be greater than the gap between these two close obstacles. So even though this seems like an ideal place for the car to travel, it really is not. So a better way to approach this is to look for a threshold instead, is to see that you have a certain threshold that, let's say that I have my threshold distance to be 5 and the number of LiDAR scans that I want to look at to be 3. This means that any distance point that is greater than 5 is a suitable, becomes a suitable point for the LiDAR to follow. So for example, this would be considered a close obstacle, but the next 4 points on this would not. These would be considered to be a large gap. On the other hand, this would be a close obstacle. And even though this point comes in between two close obstacles, it is only one single point. We need at least 3 or more points in order for it to be considered a suitable gap for the car to follow through. So ideally, these are the 2 different gaps that I would want my vehicle to follow through. Of these 2 gaps, this one is larger and it is also closer to the general heading direction of the car. So therefore, this would be the more optimal gap that we would want the car to follow. So the general steps in follow the gaps are to find these gaps, to determine what the widest gap is and determine what the most optimal gap is as well. So in this particular example, we see that even though we have developed like what we want from a very basic follow the gap algorithm, this is necessarily not always enough. Like as seen in this particular example, if we have a distance threshold set and we have the widest gap shown to us, sometimes this is not ideal. Like we have a gap here that we want the car to go through, but the way in which this vehicle travels, we will not be able to reach this position without colliding against these two obstacles. And this is because of the non-holonomic nature of Ackermann steered vehicles, of cars. Holonomic meaning if holonomic vehicles are basically vehicles that can turn on a whim. If I had a vehicle that only had two wheels here, if I cut this car in half, I should be able to turn this vehicle left or right without having to move the vehicle forward in order to turn left or right. And these are called holonomic robots. And such an algorithm would work very well for holonomic robots. But for car-like vehicles that need to go forward a certain distance in order to turn left or turn right, these algorithms can sometimes have drawbacks such as these. So in order to account for the vehicle safety, in order to account for these things for happening, we cannot use a naive follow the gap algorithm. We need to add modifications in order to, we need to add certain modifications to a general algorithm in order to make the vehicle move forward with good performance, with good robustness. And one of the ways in which that can be done is by trying to enlarge the obstacles around you, trying to provide a safety distance of the obstacles around you, so that to prevent the vehicle from moving forward, from colliding with the obstacle. For example, if my vehicle has a certain amount of width, I can reduce that width down to a point or a line by expanding the size of the objects around, by expanding the size artificially of the objects around you. And now Ajinkya will discuss some of the further tweaks that we can add to the follow the gap algorithm in order to make this vehicle or make this algorithm more robust.
Thank you, Adhiti. So the first tweak that we can do in order to resolve this problem of basically navigating through a small portion of area where the vehicle width might be more is to basically have an inflation radius here shown by RB. So we detect the closest point to the LiDAR, and basically the points around that in that inflation radius RB are all turned down to 0, or they can be even turned out to the minimum distance, which is 3.1 in this case. And all the other points now can be considered as the free space highlighted over here in the orange dashes. So the next step is basically in this free space, we find a continuous stream of non-zero objects in that LiDAR scan. This portion highlighted here in green, this now basically represents the gap which exists in the environment, which we aim to follow. And in this gap, the best approach would be, like the most naive approach would be to follow a point which is furthest from the car. And that's what we are doing here, where we choose a point which is furthest from the car. In this case, it could be something like 10.1, and basically try to follow that path. And we do this recursively. But now there comes a question that if the obstacles are relatively far away, do we need to swerve and basically change our target point at every instance? And this is the reason in the previous approach, in the naive approach, what you saw as the vehicle motion being wobbly around obstacles. So in this tweak now, what we have done is that selected the closest point to the vehicle, then in that inflation radius, like adding like a C obstacle space to the obstacle in front, we have filtered out the area which we call a gap. And in this free space, now we are selecting a furthest point where we try to track. And in this video, we can see that the result being that even though it tracked the obstacles beautifully, but when we have a relatively open space, the car is still wobbly because it's switching from one point to another in order to navigate the environment. So to overcome this, the people from the UNC team, who are the winners of the 2019 F110 Grand Prix, they came up with a different approach called the disparity extender approach. So as a modification to the follow the gap approach, what this disparity extender algorithm does is basically, as opposed to finding the closest point to the vehicle and having an inflation radius around it, it basically just goes for the furthest point from the vehicle. And what will happen in this case, if you just select the furthest point, is that the readings you get from the LiDAR is by assuming that the LiDAR being a point object, and it doesn't consider that vehicle has its own width and its own dimensions. And as a result, if you just try to follow the furthest point in your environment, you're certainly bound to hit some obstacles which you haven't considered for. So for this reason, similar to adding an inflation radius around the obstacle, what we do is we create something like an inflation radius pertaining to that gap, where we basically find the disparity in the readings in that particular window, hence the name disparity extender. As you can see, the blue arc is basically, we are trying to filter a specific range of distances, which is defined by the threshold around that point of maximum distance. And we find that as we go left, there is a curvature in the path, which will naturally bound us to hit that. And once we have seen that there is a curvature or a restriction to go in this area, what we do is basically find the minimum distance in this inflation radius, and then modify our LiDAR scans to basically map out the minimum distance in that particular area. In this way, we do it for the whole gap and basically find a point where the minimum distance around it is greater than its adjoining points, thus effectively finding out the point which is at the maximum distance from the vehicle, but also is traversable given the width of our vehicle. And this approach can be seen here live in action in the 2019 F1 10th competition. Since this is a longer video, I'll just show a snippet of it where it's working and going around the track. And as we can see, the vehicle is pretty fast and it's able to react really quickly and find out the gap which it can traverse feasibly. And this can be also seen in the simulation, where they basically tested the disparity extender algorithm in this track. All right, so there's another tweak which we can do, is that is control of linear velocity while we are navigating through our environment. And in this step, we can also use a greedy approach using an optimal reactive approach for dynamic programming, where we can basically find out different gaps, calculate the disparity extension, and then based on this, generate a velocity profile depending on the distance to the gap or the furthest point. And in this way, what we can get is a piecewise linear optimal policy to go from one point in the environment to another and do it recursively while mapping out the disparities. And this is the same video where they did the final lap, and there was an obstacle in the road, and the algorithm actually pretty quickly detects that and swerves around it to avoid obstacle and carry on with its racing. So as you can see, reactive approaches like this can be pretty fast. And this is a first-person camera view of the vehicles racing each other in the final competition. I'll just take it ahead considering the time. So the vehicle considers the car in front as an obstacle, and at every time step tries to figure out its way around it, thus basically trying to overtake it and then continuing on with its lap. All right, so one area where this disparity extender algorithm can face some challenges is during the cornering, and especially if you have very steep corners. So for that, an extension to this approach is to consider LiDAR scans below -90 or +90 degrees of the car. In this way, we have a little preview of the distances which are behind our vehicle, so as to, if we find the maximum possible gap which is left to the vehicle doesn't take an immediate turn. If it senses that there is an obstacle or hindrance next to it, and thus keeps on going straight to avoid that collision. And another issue with this is, in the corner cases where the disparity extender can fail, is that even though you know the correct path to follow is going left through the corner, but depending on the angle of attack or the way the vehicle approaches the corner, if it doesn't see that we have a bigger gap right across the corner, it would directly pick the gap which it senses is the largest, here in the case shown by the green arrow on right. And if we are not lucky, the vehicle will just end up going in circle or go too further along the corner, trying to figure out a decent gap. And this can be seen over here, where if an obstacle is placed or there's a steep corner through which the vehicle can't see, it will basically pick the largest gap and try to go around it, thus causing it to swerve around. All right, so in order to mitigate this issue of basically having variance on the performance in sharp corners, we basically do some modification in that we consider, we try to mitigate the wiggling problem, wherein we set a max threshold. And in this threshold, we basically try to follow the center of the deepest gap as opposed to swerving at every time instance. And this way, in long corridors, we can ensure that the vehicle can go straight and basically have a decent approach to the corner where it could see the largest gap and take a turn in time. So this has been deployed, as mentioned before, in race settings and reactive methods, since they don't require explicit map and can be really fast. And you can tune it really easily, have been really popular for racing. And in the later stages of the course, people have also used imitation learning and other deep learning based approaches to basically come up with strategies for following the gap. I would like to now hand it over to Ameya to basically talk about the OpenAI gym and following the gap and other algorithms.
Thank you, Ajinkya. Am I audible to everyone?
Yes.
All right. So this method, follow the gap, Adhiti and Ajinkya both discussed how the theory works. The practical implementation of this method has now been made available as a part of the course as well. The links you can find in the chat window, which Dr. Krovi just put in a couple of minutes back. So the idea is, if you had, let's say, a Python script to develop this code, you would do things like initialize your agent, you will initialize your driver, basically. Then you would set up the AI gym. This would be like a simulator engine. You will set up the engine. If you want to add more drivers or more players, you would add it to that. You will set up what their starting points are. And now you will develop the code and basically make the vehicle run for a couple of laps. Now you will do this in loop while now trying to use the process LiDAR function and somehow try to optimize it. The idea is this, that whatever theory-based code, which you have came up with your follow the gap code and the various tweaks which you have done to it, it is always a nice idea to first try it out in a simulation-based environment before jumping on a real car. Now, Dr. Betz over here has now created a free tutorial session for this follow the gap coding thing, and this is accessible to everyone on YouTube. He has provided links to the repository where you can find the basic code, the skeleton code and outline, and then walk through it line by line to set up your follow the cap algorithm. At the end of the going through the entire code and working it together, you can now set up your follow the gap algorithm in a simulation based environment, and then finally tweak it to if you want to deploy it on actual car. So now this is available on YouTube. You can go around along with the rest of the course materials. This is one of the deliverables. All right. So follow the gap is one technique. It's a nice technique, but there are some other variations of reactive planning approaches which are also available. Common among them are bug algorithm and the potential field approach. So bug algorithm, just like you can see in this video over here, is something similar to how a bug travels. So it gives you an idea of how this algorithm might be working. For this bug algorithm, the information that you need is a destination, a global destination, and second, information about what the obstacles are around you. So how does this algorithm work? So the basic idea is starting from your initial point, you would do the laser scans and find out distances to various obstacles. Once you find distances to various obstacles, you can select them as endpoints and draw a segment through these points. In this picture over here, you can see that the green ones are the points which the agent has noticed, and the blue is the line which it draws between those points. With drawing these lines, it understands, oh, this is a no-go zone. You shouldn't go over there. Whereas the sector between the points B1 and B6 is like an open area, and now you can proceed to it. Okay, now you have found an open area. What to do next? Once it proceeds a little further in that open area, now it hits and sees a new obstacle or a new wall, which is now segmented by the lines B7 and B8. Now, how do you proceed? So it knows that it can't go through this area. So this is where the global destination comes into play. Using the distance between your location, the points of the obstacle, and the global distance, now you can formulate something known as a total distance, a heuristic. Now, this distance would be a summation of the distance between the goal and the obstacle distance, as well as yourself and the goal distance. Using these values, now you can find out what is the minimum distance, the minimum heuristic, and now try to go towards the goal. But again, there are challenges with this algorithm. So this is the idea, basic idea. So in the first time step, you would approach the obstacle, you would find out, oh, there are two different ways you can go about. You will go a little further, and slowly now you will follow that entire obstacle and move towards your goal. So the basic disadvantage are sometimes it generates long trajectories. Another challenge is that if you want to calculate this global heuristic, you also need the information about what that goal point is. If you decide, okay, I don't know what my final goal point is, so let me pick up some goal point in my entire space, then how do you come up with this local point? This is another challenge. Similar to this method, what you also have is the potential field approach. The potential field approach is similar to the bug algorithm, but now you can see when your vehicle, your robot is now traveling through the obstacles, it somehow flows through the midpoint of obstacle, or at least seems to go through those points. So what is this approach and how is it different from the bug algorithm? So the idea is that you distribute your entire space into potential electromagnetic potential fields. So you have the obstacles will be given by, let's say, a positive charge, and the vehicle itself will be given by a positive charge, and the goal will be given by a negative charge. So the positive and negative attract, that's why you try to move towards the goal. Whereas since positive repel, you move away from the obstacles. So this is the basic gist of how you would develop your potential field approach. This is like a binary way, but now you can also implement something known as gradient descent algorithm, in which you try to steer away from the high peaks, which are like peak positive zones, and then try to move slowly slide inside towards the negative zone, which would be your the goal point. So at every time step, you would calculate the gradients and then move towards where the gradient is minimizing. So again, similar to the bug algorithm, this approach also has its own problem. The basic problem is that you will have to calculate the gradients repeatedly, so it becomes computationally expensive. What other point is like, again, you need to know what the global point is. So from where you are and where you want to travel. If you don't have the global point, if you decide to choose any local point as a goal point for a particular time step, then how do you choose this local point is another challenge with this. You can find out more information about this. But these advantages, because of these certain disadvantages, these methods are usually avoided, and follow the gap and its various tweaks are now an efficient way to go about it. So in general, the challenges which come with the other methods as compared to follow the gap are, it's difficult to find the global goal point. And with the follow the gap, it is now easier to navigate your environment as compared to these methods. That would be end of this session on reactive plannings. I would ask Dr. Krovi to proceed. Thank you.
Thank you, Ameya. Let me, if you would stop sharing. So one of the things that you probably saw in this session was how the combination of the simulator and the physical platform became a powerful tool to evaluate a number of alternate options. In particular, I think it starts here, but as you go to even more complex algorithms, being able to test it in simulation becomes a very crucial tool. I think as Rahul puts it, the simulator was an innovation that people had started early on to try some things out. And then it became the de rigueur, the de facto standard by which all the students would fine tune their algorithms, the different coefficients of the algorithms, and then deploy it with almost minimal changes onto the final vehicle. The other opportunity that I think we'll see different people highlight as you go through this course is that you have varying grades of simulators that are available, and being able to pick the right simulator is crucial. So in this case, because it's a LiDAR based operations, you could now take advantage of the lightweight simulator that was again developed by Penn, and the f110.org website has the links to that. But I see that Dr. Madhur Behl has joined us, so I'll invite him now to tell us a little bit more about the pure pursuit part. By the way, before I turn the things over to Dr. Behl, I wanted to highlight that Dr. Behl has himself put up a number of lectures on YouTube. I hope he'll get a chance to tell us a little bit about it and maybe share some of the insights and how he deployed it during the pandemic and how it's become a super hit. So without too much further ado, I'll stop my share.
All right, thank you, Venkat. Let me quickly pull this up. All right, hey everyone. I'm Madhur. I'm an assistant professor at University of Virginia, and Varundev Sukhil, who's my PhD student, was supposed to give this talk, but he's actually interviewing for an autonomous vehicle company on the West Coast today, so he couldn't be here. But I'm happy to discuss pure pursuit. So as Venkat was saying, I have been involved with the F110 since the very beginning, since the very first race in 2016. And over the years, the community has just grown by several order of magnitude, and it's great to see continued interest in becoming part of the F110 family. And we actually hope to see many of you in our future competitions. That's one big point of this exercise, to grow this and get everybody together. But I have been fortunate to also transfer some of this work that I started with F110 onto the full-scale race car. And I'm the team principal for the Cavalier Autonomous Racing Team, which is one of the teams in the Indy Autonomous Challenge. And we had the experience of racing this full-scale Formula One style car at multiple racetracks last year. And one of the things on the meta theme I want to actually touch upon is how these principles of perception, planning, control that you've been learning about in these tutorials, they actually transfer very well to across scales. Of course, things become complex, but the fundamentals are common across all these themes. So with that, I want to dive into a key question of how do we actually follow a point, right? So we keep hearing go to the middle of the gap, or try to pass your opponent, or steer towards this direction, steer towards that. So the idea is how do we actually follow a point as an autonomous robot, as an autonomous vehicle? So to kick off that, let me play a video, and give me a second here because I should actually reshare with the video optimization on, so that it will play smoothly for you. So this is just a small snippet of what the car can do. Actually, at high speeds, you can go so fast that the wheel comes off the ground. You can see in the slow motion diagram or the video here that the car is going so fast that it's tilting, but it's able to maintain that balance and come back. And then here, what you are seeing is we have two agents, and one of them is actually trying to figure out and predict where the other agent is going to be. And it's going to synthesize a path to overtake the opponent kind of on the inside, like racing drivers do. So here, we are distilling that into a set of sub maneuvers, but you can see how it can track the car, find this opportunity to overtake, and then just, step on the throttle a little bit earlier and get out of that corner soon. So like Venkat said again, simulation is definitely a key to implement many of this. And so here you can see what that looks like in simulation. This is not the exact scenario we saw in the video, but you can see the car is trying to overtake on the outside in this case, and then merge back to this kind of reference trajectory, which is shown in the solid red line. All right, so the science behind this and how to do this and many of these maneuvers relies upon the ability of the race car to go from its current location towards a waypoint, or towards a target, as we say. And the idea, one of the ideas, there's many ways to do this, but one of the simplest ideas behind how to do this is what is called pure pursuit, and that's what I'll try to describe in the next 20 minutes or so. So what we are assuming here is that we have a race car, our FR10 race car, and we are given a trajectory. A trajectory in robotics is just a sequence of waypoints. So waypoints are, X, Y coordinates of positions that are sequentially laid out on the track, and that will, could be corresponding to, let's say, the race line that you want to follow, the, fastest lap to get your fastest lap time, or a trajectory you may want to follow to avoid some static obstacles and things like that. So we assume that there's some algorithm, some oracle, or some mechanism for us to obtain that trajectory or a sequence of waypoints. And then we can derive, the XY position of any waypoint in our own inertial frame, or in the frame of reference of the vehicle itself. So our goal is to now track or follow these waypoints, and that's what pure pursuit allows us to do. So if we formalize this a little bit, we can see that we can imagine that the there is a coordinate frame which is located at the center of the rear axle of the F-110 car. This in robotics, by the way, this is a special position in robotics for car-like robots. It's called the base link. So this base link frame is placed here, and in ROS especially, there is the convention of the right-hand thumb rule. So X is forward in this case, so Y would be leftwards. And also remember in ROS that RGB color convention is always XYZ. So if the axes are not labeled, but they are colored, we can still figure out what's going on. So this is our race car, and it's just kind of driving forward in the x-axis. And we wanted to now drive at a certain desired goal or desired distance away from us. So we define a look ahead distance as the distance between where we are right now and in this picture where the goal is located. So we want the car to steer right and somehow figure out how to drive towards this goal. So how do we actually navigate and figure out how to steer? The idea behind Pure Pursuit is, given this goal and given the value of the look ahead distance, you will try to define some arc of a circle that drives the robot towards that goal. Okay, so why is this an arc? Why can't I just follow the straight line? Because, as was also said, I think previously, our robot is non-holonomic, meaning that it cannot just spin about. If it spins about a single point, it means the wheels are sliding about. This is not what we want. So as you steer a car, it's also driving forward. So what you will actually trace is this arc between your current base link and the goal point. So we want to follow this arc. And if you think about it, this is not very different from how you and I drive, right? So when you are driving, you are not looking at immediately what's in front of the bumper of the car, right? That's not how anybody drives, or at least I don't recommend it. So the way you drive is you actually have intuition for looking ahead a certain distance, and you steer according to that horizon that you define according to how fast you are going, what is the traffic situation around you. So this is sort of inspired from to mimic that behavior. We have a look ahead distance. We want to steer towards something which is forward projected, or it's in front of us, not immediately in front of the bumper of the car. So we want to follow this arc intuitively. And the idea now is, well, how do we find this arc, right? So like one question is that, is this arc unique? Is this the only way I can trace an arc between my current position or the goal? Well, obviously the answer is no, right? There's actually infinite number of arcs that could go from between these 2 points. So this arc is not unique, which begins the question, if you have many options to choose from, which one would you prefer? How is one better than the other? And so the idea is that we will want to make or find a unique arc. So let's look at a very intuitive illustration that will clarify how these different arcs result as a consequence of how much we steer. So here in this picture, you see that, let me kind of tell you what is going on. So our robot has been just condensed into what is called a bicycle representation, right? So we are not showing all 4 axles and the entire rectangular frame of the robot. We just assume there's a rear axle, there's a forward steering column. And so you can see as you turn left, in this case, towards my goal point, or TP means target point, based on how much I'm steering, my car will actually trace this orange trajectory, or in particular, the center of the rear axle where I placed my coordinate frame, the base link, it will trace this orange trajectory. That's the curve that the base link will follow if I steer by delta. And so if my goal is to go until the target point, I have to steer more or less. So let's see what we have to do, right? If delta decreases, if I'm steering less, I can traverse an arc which is larger radius of curvature. So R has increased by steering less. If I keep steering less and less, there will exist a value of how much I have to steer from my current position such that I can find a unique arc that will go through the goal point exactly, right? So in this case, that delta would be 11.5 degrees, right? So you will find this delta so that about the instantaneous center of rotation, that's what ICR means, you are traversing this orange arc that is driving you to your goal, which is what we wanted to do. So what is the trick to finding a unique arc? It's just that you constrain that the instantaneous center of rotation should be along the axis which is aligned with your base link. So in this case, we are saying that we constrain the center of the arc to be on the y-axis, and then that will give us the value, or it will give us the unique arc that we have to traverse until our goal point. Okay, so now we have this geometric view where we have a radius of curvature. It's still not clear yet mathematically. How do you actually turn, or are you turning based on the look ahead distance or the XY values? So how do you translate this nice intuitive idea into something you can implement in code? And so geek out with me for a second here. We can derive how much we have to steer exactly. So what we do is, in this picture, we first say or observe that what is radius, right? So this radius R is the sum of Y and D. If you look at this bottom part of the axis, R is just the sum of Y and D. And also from this, Pythagoras theorem on this right-hand triangle on the right, we see that x square, x is just the x coordinate right here, the vertical line, plus d square is equal to r square. So we have these two equations. Here you can eliminate and solve for d. So we do some very basic algebra. And you also notice that from this right-hand triangle, L square is equal to x square plus y square, right? So we have both these relations which hold in this picture. And what you can solve for is really that the radius of curvature of the arc that you have uniquely defined would be equal to this expression, would be equal to the square of the look ahead distance divided by a measure of how laterally away you are from the goal point, which is y in this picture. Okay, so we have this idea. So how do we turn this into some way of controlling the steering of the car? So what we say is that, remember in that picture that I showed you where the steering was reduced and you were able to go through the target point. So if you recall, we were reducing the steering and the radius of curvature was growing. So delta, the amount by which you steer, should be inversely proportional to the radius of curvature. And that's exactly what is shown here. 1 by r is defined as curvature of an arc. And so you steer proportional to the curvature of the arc. And that really is what pure pursuit does. Okay, from your current position with the look ahead distance, with the XY of your goal, you steer proportional to the curvature of the arc you want to follow. So if it is a sharp arc, you will steer less. If it is a more or less straight line, if it's a more or less straight line, you will hardly steer. And if it's a sharp arc, you will have to steer aggressively. So we have answered, or at least intuitively understood, how do you steer? There is one more question which should arise, that how are we actually tracking where the points are? Or how does this look ahead idea map to the trajectory idea that I started off with, right? So trajectory is a sequence of waypoints. So in particular, the idea is that how do we pick what is our goal, or how do we pick, which should be a target point from a given set of trajectory? So let's try to navigate our head around this particular question. So here is some cartoon trajectory, and this is what a waypoint is. It's just a single point in the sequence of waypoints. And so a car is located somewhere here. We want to drive towards the waypoint, and we just saw that we defined some look ahead distance. It should be fairly obvious by now that look ahead distance is a design parameter. Okay, this is your choice. Pick what you want. It could be 6 car lengths, 5 car lengths, whatever you want, right? Or later you will see, I will give you an example where it can even be adaptive. It doesn't have to be fixed at all times. But let's get back to the question at hand. We are given a look ahead distance. We have to find what is our goal. So in this picture, if I ask you, well, what is our goal, right? Our goal will clearly be this point, through which just happens to be by the magic of PowerPoint, reside on our exact circle where we wanted to look ahead. So this is a very obvious case. We have found our target goal, and we can solve the previous relationship to get the value of the radius of curvature and steer proportional to the inverse of the curvature. Okay, so we pick the waypoint that's obviously closest to where the vehicle is, a certain look ahead distance. We will drive towards this look ahead distance. We may not actually reach it because we can keep repeating this algorithm. You drive a little bit forward, and then again, a time has come to make a decision. Let me look ahead another distance L, see what is my next candidate waypoint. So sometimes you will not be so lucky, right? You will actually, this will be most of the times you will not be lucky that you have an exact waypoint defined, the exact look ahead distance at every point in your racing line. So in this case, there's many things to do, but let's go with the most intuitive and straightforward thing. In this case, I can actually, what I can do is I can pick either the look ahead distance, which is just outside. What is the next waypoint, which is just outside my radius? which would be, this point in this case, or a more rigorous way would be, I can actually interpolate between two successive waypoints, one which is just inside, one which is just outside, and actually derive the coordinates of this pseudo waypoint that did not exist originally in my trajectory, but I'm creating it so that I can solve my previous relationship to govern how much to steer. So I can obviously interpolate between these two waypoints. Right, so I hope that idea is clear. And so how do we actually put this together? We are at a given location and we are given a trajectory, which is a sequence of waypoints. Given a look ahead distance, we calculate what should be our goal, what should be our target, based on what I just showed you, interpolation or closest, nearest neighbor, what have you. Then you actually drive, or pure pursuit is just, controlling the steering. So pure pursuit is what we call a lateral controller. Because if you notice, I'm not calculating how fast we are driving towards the waypoint, which would be what we call a longitudinal controller. So we are just controlling the steering angle. So this is a lateral control. So we actually control or actuate the steering column towards that waypoint. And as we are driving towards it, we do another iteration of this loop. This loop could be the control loop of our robot. And essentially we are then localizing to find where we are, and we are repeating this entire process. So visually that would look something like this. You have a goal that you just derive to drive towards. You drive a little bit forward, you find a new goal. You drive a little bit forward, you find a new goal, so on and so forth. And ultimately, if you trace how your car has driven, it may not physically pass through every waypoint. Actually, it's very unlikely it will pass exactly through the waypoint unless it's a straight line. But it is tracing the profile of your trajectory. That's what tracing a trajectory is. And you can actually define certain things, that how closely you want to track the trajectory versus, how smooth you want the profile of the car to be. Okay, so that in a nutshell is what pure pursuit does. So let's understand the effect of this look ahead distance. If you notice, that's the only design parameter. I'm not assuming anything about, what is the wheelbase of my car. I'm not assuming anything about what are the forces on the tires and things like that. So it doesn't use a model of the vehicle, but it's able to steer because we have a goal and we know where the vehicle is. We have the basic information. So the only thing we actually have anything, a way to control the behavior of the car is the look ahead distance. That's the sole parameter within the seminal pure pursuit. And so if you think about it, a smaller value of the look ahead will result in very closely following the curvature of the arc, because you're not looking very further apart. So the closer your waypoints or goal points are, you are making very minor adjustments to the steering. So you'll be closer to your desired trajectory, but it may lead to very small radius of curvatures. And remember that the radius of curvature is inversely proportional to the steering input. So you may have a very tiny arc because the look ahead was so small, and it may result in very extreme steering. So it could result in arcs that are actually not feasible to be tracked by the steering column of the car. That's what it is meant by that it might be against the dynamical limits of the vehicle itself. What about the other case, right? Why can't we just look as farther as possible? The problem with that is that, yes, if you look very far, you will get a very smooth steering because you are not, reacting to the noise of one waypoint versus the other. You are looking, 100 meters ahead, 200 meters ahead. The issue is that your ability to track the line, the reference trajectory or the race line will be compromised. So the further you look, your car will try to cut corners, right? So if your race line bends towards the left, it will try to cut corners because the look ahead distance is not an arc. The look ahead distance is, straight as the crow flies. It's just a straight line. So it will try to go straight towards that point with the arc, but your arc may not align with the reference trajectory. And so it leads to, this corner cutting behavior. And I'll show you a video which actually convinces you of this. So here is one idea to, fix this behavior, that pure pursuit doesn't take dynamics into account, and it might produce infeasible arcs that we have just noticed. I mean, it will get the job done for the most part at slow speeds, for the F110, if you're just learning pure pursuit, it will work very well out of the box, but there is room for improvement. So let me show you one of many ways in which you can improve pure pursuit. The first idea is what we call Ackermann adjusted pure pursuit, or we have, instead of assuming that we just have the knowledge of the base link, we actually assume that we know something about the geometry of the car and where the steering column is located, what is the wheelbase, and things like that. And when we take this geometry information into account, we can do a little bit better, right? So we can track the reference trajectory. It is not really a full-blown, kinematic model of the car at this point. It is just adapted, we are using what we call a quasi-model version of pure pursuit. And in fact, the reason why we do it is we are adjusting for this Ackermann behavior. If you're not familiar, Ackermann steering is the same as, what we call non-holonomic steering. So your car that you drive cannot spin in a circle of 0 radius, right? It will take some, basically it has a minimum corner radius that it can achieve. And that's because how the steering column links work. So what is this Ackermann steering adjustment to pure pursuit? We assume we know the, the wheelbase of the car, and we know that the steering column can, have some range in which it can steer safely. And then we use this information and combine it with the knowledge of, that we have to kind of trace this arc inversely proportional to the radius of curvature. And I haven't gone into super detail in the math yet, but basically what we are doing is we are incorporating the steering column, and we are calculating the steering error from the front axle. So we are only turning the front axle of the car to get to a point, and we are now using the position of the rear axle as a feedback mechanism. What that means is, when you turn the front axle, the arc is getting traced by the rear axle, right? So that acts like a feedback mechanism. It's feedback because if you are oversteering or understeering, it will the error will grow or reduce based on the difference between the position of the center of the rear axle and your reference trajectory. So putting everything together, you can directly solve for how much you have to steer with this Ackermann adjusted pure pursuit as this expression. And I apologize, there's a notational confusion here. Here, capital L is not the look ahead distance, it's the wheelbase of the car. It's the LD is my look ahead distance, right? As is shown in this figure here. So LD is the look ahead distance, which should be in the denominator. Okay, so we can now do something better than seminal pure pursuit, but we haven't addressed this issue, right? So the previous improvement was so that the arcs we are generating are dynamically feasible. We don't run into the issue that you're generating a steering request that your car cannot entertain. But now the other important point is, how do we pick a reasonably good look ahead distance between this trade-off between how closely we track and how smooth we want to the steering to be. So here is one idea. And again, this is from work that my student has done. And what he basically has proposed is that you can look at this picture. Let's say there is some section of the track where the car enters here in the black footprint and this black dot on the top. This is where it is spawned, let's say, in this section. And then the solid line is what we want to follow. The red is my goal on the reference trajectory as denote, set by a particular look ahead distance choice. And then I define like an exit point where I would say this section ends. So this section is basically how the car navigates this left-hand turn. And what we can measure is a couple of things, right? So the car will actually follow this dotted line as it traverses towards the goal. And what we can immediately measure is what is the cross-track error between how you traversed and where you were supposed to be, right? So what is the error or the area between the solid line and the dotted line? So that's a measurement of how closely you are tracking the reference trajectory, which is called cross-track error in robotics. And the other thing we can also measure is that if you choose a particular look ahead distance, what is the exit velocity at which you will exit this sector or exit this piece of the track? So we have two things that we can measure for a given choice of look ahead. We can measure how closely we track, and then we can measure how much speed we would gain by not tracking closely. So the smoother your trajectory, the less your steering input, the faster your exit speed. And when you put everything together, you can run an optimization and you can solve for the optimal value of the look ahead distance given the geometry of the racetrack and a reference trajectory. What that means is the following, and this is close to the end of this tutorial, so I'll wrap up soon. We have a real racetrack. This is the racetrack I have in my lab at University of Virginia. what we can do is we can use any of the mapping methods that you will learn about or have been mentioned before to first create a 2D occupancy grid map of this track, right? So this is what the track looks like from the LiDAR point of view. And then we have developed this pipeline that can ingest a 2D occupancy grid, and it can automatically detect the edges of that grid and extrude them into a 3D mesh, as is shown in this illustration on the right. And then we can import this mesh as a STL object into a simulator called Gazebo. Gazebo, is a simulator that is used by the ROS community. It is different from the lightweight simulator, but the 2D simulator. So here, the benefit I would say of using or knowing Gazebo is that it has a lot of different physics models that you can just incorporate into and you can place obstacles very easily into this environment, and it is very compatible with ROS. So we have gone from real world into the map, into the simulation of that real world. Within the simulation, we will run an optimization to label this race line such that we use different look ahead distances based on different parts of the track or different sectors. And then we will export those labels into the real world again and have our F110 car actually go faster or track the trajectory in an optimal manner, right? So this is an entire framework that you can think of as going from real to sim and then back to real. So how does it work? Very quickly, here are two examples. The illustrations will tell you what is going on. The top one is a labeling assignment, which prioritizes going faster. So green means a longer look ahead, red means the shortest look ahead, yellow is somewhere in the middle. So you can see if we want to go very, very fast, we need to have more regions where we could use a longer look ahead. And during the very sharp turns, we have no choice but to use a slightly short look ahead. The trajectory labeling on the bottom means that the regions where we are red, we would be tracking the reference line very closely. And the regions where we are yellow, we would not be tracking as closely. So there is no green on the bottom because this one prioritizes tracking error over exit velocity. So you have all these competing objectives, right? So if you increase the look ahead, something good happens, but you lose something and vice versa. So now you can start thinking of combining this as the best of both worlds. You could say, I want to weigh 50% speed, 50% tracking, or I want to bump up the speed parameter. So it could be a convex combination of both of these. And so let's look at how this works. So you can see that, we can generate this multi-label look ahead distance. So you can actually notice carefully how the look ahead increases or decreases based on how the reference trajectory is colored. Colored is just the assignment. So those waypoints have the short look ahead in red and the largest look ahead in green. And our F110 car is using pure pursuit, Ackermann adjusted pure pursuit to then follow this reference trajectory. So we can do this in RViz, which is a 2D view. And like I said, we can import a real world track automatically into Gazebo. So you can, really test your pure pursuit, improve, make adjustments in simulation. You can crash many, many times in simulation. So you don't have to do that in the real world. And then you just export this directly onto a ROS node on the car and everything comes together. This car has now figured out how to dynamically use different look ahead distances as it navigates its way around a pretty complex track, right? It has a lot of sharp turns, but this is doing a really good job of going around. All right, so this was F110. I want to conclude by telling you a little bit about what, this extraordinary claim I made in the beginning, that you could translate this to the full scale car. So here is a very quick example of how some of this can be applied to the real world. So this is an aerial view of the Las Vegas Motor Speedway, where a previous Indy Autonomous Challenge was held. And so what we do first is using, we don't have to create a 2D occupancy map of this track. It's a real world, really big track. And, that has a whole different bunch of problems and how do you map with a 3D LiDAR and create a good map of the real world. But we will just need a semantic map, right? So we only care about where the bounds of the track are. So we have the inner bounds, the outer bounds, and the red line is a race line. I believe Johannes will talk about how the race line is derived and how it's used for planning. So, we have this race line in the track, and just like we had a reference trajectory in the F110 car, And now we want to follow this trajectory, right? So instead of the F110 simulator, here we are using a simulator called LGSVL. So you can see on the right-hand side, the visualization of a very basic pure pursuit, Ackermann adjusted pure pursuit, right? You can see that red bubble is the look ahead point that it's trying to track, and it's actually doing a very good job of locating the base link directly on our reference trajectory as this car drives around the track. And so this is, again, from that map to simulation, and then we can actually do this in the real world. I will say it is not advisable for a real race car to just use pure pursuit. Remember, the limitation of pure pursuit is it has no knowledge of the dynamics of the vehicle. It has just a geometric lateral controller, right? So a more suitable controller, a more advanced controller that takes into account the tire forces and how much the power is being given to the car and how much torque is being given to the car is a model predictive controller, but that's obviously out of the scope of this particular tutorial session. So let me show you two examples. One, I will show you an example of corner cutting in the real world, and then I will show you an example where it actually does a pretty good job. So here you will see, this is the real race car, and this is what corner cutting looks like in the real world. So you see how my wheel is out of bounds, and actually even my nose is pretty much out of bounds. It's very risky. The car could have easily lost traction and spun. So that's why, this is just an example. We don't use pure pursuit for the real car anyways. We use a MPC limitation in the real world, right? If the look ahead is not tuned, this is what corner cutting looks like. And in the situation when everything works as expected, this is a well-tuned pure pursuit controller. It's not going super fast. I think we're just going maybe 90 miles an hour in this video, which is much faster, by the way, than freeway speeds, but this car can go up to 180 miles per hour. So it's almost half the speed. But this actually, believe it or not, is from last year where we were still using pure pursuit. And you can see it's very stable. The steering inputs are not crazy. It's not oscillating. It's tracking the waypoints. The waypoints are specified in GPS, lat long, but we convert it into Cartesian XY as well. So basically, what you learn in F110 will be tuned in F110, and all the principles still work for the full scale car. So I will stop here. I don't know if you want to take questions now, or I'm happy to take questions, email me as well. But that is what pure pursuit is for autonomous racing. Thanks.
Thank you, Dr. Behl. And I think we have enough flexibility to open up for question and answers if there are any.
Sure.
And if not, could you also highlight about your YouTube tutorial series so people who are online can maybe just go ahead and check that out?
Yeah, I'm happy to. So if you just search F110 UVA or UVA University of Virginia, or I think if you just search for my YouTube channel, just type in my name, you will find a series of videos that I have been recording, because I also teach the F110 course here at UVA. It's a senior undergraduate course. I'm actually teaching that this semester. And yesterday they did their follow the gap assignment in the real world. And it was very fun because they were driving around and we were throwing foam cubes in the middle of the track because they don't need to know, right, where the obstacle is. It should be able to detect the gap in real time. So all the lectures are available. I think the F110 website has done a really good job of putting all these resources together. So it is a one-stop shop. And now recently, Johannes and a lot of folks from Penn have improved the quality of the lectures and putting everything together. So we've done all the hard work of preparing all of this, stuff for you. And so all we are requesting from you is time, right? So just sit down, go through the videos. They're very interesting. They're very intuitive. And when it's needed, you go into the math. When it's needed, you go into the simulator and the programming directly. But we always keep track of the big picture, right? We are trying to teach the principles of perception, planning, control in the context of racing, which makes it very, very exciting. All right. Thank you, Alex. I see your comment. Thank you if you like the videos on YouTube. Is there any tuning?
There are a few questions in the Q&A and the chat.
Okay, just does pure pursuit take account of obstacle? No, so it is just the controller, right? So if you have perception, planning, control, the planner has the burden of dealing with, I should not hit anyone. So planner will give me a trajectory that will not go through an obstacle, and pure pursuit will ensure that I follow that trajectory in a manner that is capable based on the dynamic setup of my car. Is there any tuning model for pure pursuit similar to PID given by MATLAB? Not that I'm aware of. The look ahead is the only parameter that you really can tune. And the follow-up question on how these experiments are done, there is a paper on adaptive look ahead pure pursuit. If you Google just these keywords, it will come up. So it is done in using dynamic programming.
I think there was one more question. I think two more. One from Daniel.
Oh, I see it. Okay, why is the look ahead distance changes from long range to short range on corner entrance instead of there being a mid range as we get closer to the breaking point? So it's a trade-off, right, Daniel? So the behavior of the label or the look ahead distance will depend upon what you are prioritizing. If I really want to track if I trust my Raceline that, I want to hit the apex and there is no mismatch between the geometry and the model-based derivation of the Raceline, then, my Raceline is trustworthy. I will reduce my look ahead to prioritize tracking. But if I want to also be fast and just hit the apex more or less, accounting for any other assumptions I have made, then a mid-range is what the output of the algorithm is. MPC is a nice controller, but there are other suggestions. Yeah, there is LQR, very good. Subhash, yeah, that's very right. So LQR is definitely a good controller. There's also something called Stanley controller, which is very similar to this Ackermann adjusted pure pursuit, but there's some differences. What are the key challenges? And Ajinkya, let me know whenever you want me to stop because these questions are coming in, but yeah. I'll take one more maybe. So can you highlight some key challenges when transition to a full-scale vehicle? Okay, so like I said, the principles translate, right? So MPC is MPC at every scale, but the model is much more complex. So it took us a lot of effort to tune our MPC or figure out what the model predictive control should be. Also in the real world, you go from 2D LiDARs on F110 to 3D object detection with point clouds. You have many sensors. You have camera, you have radar sensor. On my team particularly, we were not experienced with using radar, but I know some teams were incorporating or fusing radar. And just the differences that the setup of the car and the sensing modalities are much more complex, right? So F110, we don't use GPS, but on the real world, you need to use GPS. You need to convert using some geodesic into XY. So the math is a little bit different, but there is equivalency, right? So at the end of the day, if you have an algorithm that, is a planner that can overtake, that planner logic should still work in the real world in the full scale. So the key challenges are you have to put in more work because the sensing data is more high dimensional. The software stack is much more complex than the F110 stack, but the principles of the planning and the control, the planning and the control translate to a higher degree, I would say, than the perception part in F110.
Right. Yeah. Thank you, Dr. Behl, for the great lecture.
All right. Yeah. And thank you, everyone. And yeah,
your YouTube series as well as UPenn series has been a boon for people.
And here we go. Johannes is going to tell us about Raceline optimization. Perfect segue. Take it over, Johannes.
Yes.
Yeah. Hi, everybody. Yeah, thank you very much, Madhur, for the introduction. You can see my screen, right?
Yes.
Yeah.
Okay, great. So in the next part of our lecture, I want to highlight the topic of Raceline optimization very briefly. And then I will introduce you to a planning approach, to a reactive planning approach, which we call graph-based trajectory planning. And you can think about that now we are going into a more complex region of path planning and the raceline optimization. But it's important for us that you understand that there's like much more complicated stuff that you can implement to have a more racing behavior of the car. Just briefly again about myself, I'm currently a postdoctoral researcher at the University of Pennsylvania. And in the last couple of years, I spent a lot of time in the field of autonomous racing. So I was part of the RoboRace Challenge, part of the India Autonomous Challenge, where we competed against Madhur and other teams. Now I'm doing F110s here at Penn. And therefore, my focus is on path and behavioral planning for autonomous systems and autonomous vehicles, especially with this kind of edge cases of the high acceleration and the high speeds. What I wanted to introduce you today first is the so-called raceline optimization. And probably a lot of you have seen a race car driving on the racetrack, for example, Formula One. And what you always see is that this car is not just like driving in the middle of the track or driving on the wide left or the wider right. The car is driving a so-called race line. And the race line, per definition, is the fastest way to get around the track. And now you can imagine that this race line is different. When you change the car, for example, a Formula One car has a different race line than, for example, a go-kart. And you also need to understand that the race line can differ from race driver to race driver. Because if you make a special movement in one turn, it expects that you have a special movement in another turn. So when we come to the field of autonomous driving or autonomous racing, we as an engineer, we have to take care about that we define this race line. And on the right side, you can see like one example. And what you can see here is that we like cutting the corners. This is what Madhur just explained. We are like very narrow to the inside and then very narrow to the outside. That's how a race line normally looks like. And that's just like one example. And what you need to understand that we normally do that via optimization. So the question is, how do we get from a racetrack representation, what you see on the left side is just like an image from Google or a high-level bird's eye view of the racetrack, to a real race line that represents the X, Y, and coordinates that you can then follow with your race car. So the first thing you need to do, you need to get some track data, like some map data. What we provided for you is like a handful of real-world racetracks on our GitHub repository, where we had the bird's eye view from Google Maps and extracted the X and Y positions. So currently we have around 30 racetracks from all over the world in 1-to-1 scale, is when you want to drive with a big car, and in F110 scale. So if you want to drive, for example, in Spa or in Monaco or in Austin, the real world F1 racetracks, you can do that with our repository. So then you get a representation of the map, X and Y coordinates. And what you then can do is you do an optimization. And this optimization can be done in 3 different ways. The first way I want to introduce you today is the so-called shortest path problem. You probably have heard that. It's very well known as the Dijkstra problem, because what we do is we optimize for the path or the length that the car is traveling. And I highlighted that in blue, and then on the right side, you see a result of this optimization. You see that the blue line is very close to the inside of the track, just going straight, cutting the corners, and then staying either on the left side or on the right side of the track. So the shortest path is maybe an interesting solution because you travel the shortest way, but it's not the fastest way. And we try to find the fastest way. So the second option you are having is a so-called minimum curvature line. What we're doing here is we create an optimization problem that's optimizing for the minimum curvature the car is applying finally. That means that we minimizing the steering of the car, we optimizing for one apex point in the turn and then decreasing the steering right away. That's what we do. And with this one, we only have a geometric representation of our vehicle and have some very, very simple or simplifications of the vehicle dynamics, like the maximum acceleration in longitudinal or the lateral acceleration. So what happens here, you see on the right side is the outcome is like a green line. And this green line looks very, very similar to what you know as a race line. We're like moving from the inside to the outside of the corner, then going inside of the corner, we're cutting the corners. That looks very, very professional. But the last one and the most optimal one is the so-called minimum time trajectory planning. What we do here is we create a global optimal race line, which has the minimum time traveled. And minimum time, that means for us, we have the fastest track or the fastest route around the track. This is a so-called optimal control problem, which means we are not only optimizing for the path and the velocity, we are also optimizing for the control actions, which means like the steering and the acceleration of the car. So we have like this super big optimization problem. And now you can imagine from the shortest path to minimum curvature to minimum time trajectory, we are increasing the complexity of the optimization problem. For example, in the minimum curvature, in the green one, we only have like simplifications of the dynamics of the car. In the minimum time trajectory, we have like a heavyweight dynamics model of our car, so-called double track model that optimizes everything, like the pitch, the roll, the yaw of the car, and even the individual tire forces. That means you need to have like a lot of information about your car, a lot of the parameters to apply this minimum time optimal control problem. Therefore, the vehicle dynamics are very, very important. I think Madhur mentioned that before, like having the model parameters is very, very important to create this optimization problem. In the end, it's very, very simple because it's an optimization problem that you have probably seen before. So you create an objective function and you create the minimization of this object function, with subject to some constraints, either linear or nonlinear constraints, and then you optimize for that function only. And that's what I explained before. We can either optimize for the minimum curvature or the minimum time traveled. And with that, you finally get an information about the path, which means the X, Y points on the track. And even more, you can create also the velocity profile. And that's like very, very, very important to understand that only that you have like an XY point on the racetrack doesn't mean you drive that fast, because you can see, if you see like on the left side, this X and Y points, we can drive that very slow and we can drive that very fast. So what you want to have in the end is both the path and the velocity profile. And that means that we also need to optimize for the velocity profile. And there's like various techniques that you can use. For an example here, that's an evolutionary technique that has some generations and optimizes on a given path the velocity profile. Or what you can do is a so-called forward-backward solver, where you hand over your path and then it's optimizing for the turns, like going forward, going backward, and then finding the optimal acceleration for one turn. But more or less, the race line is what you want to have in the end, and that's the one you want to follow to be as fast as possible. But the race line only gives us the possibility to follow a path when nobody is around us. But what we want to do, and what you already learned today, is that we want to overtake other cars, because we want to like make advanced decisions. We want to have like blocking maneuvers. We want to make like driving behind another car, going to the right, and then moving back in again. That's what we know from like Formula One cars or Indy cars, and that's what we want to achieve. So what we do now is we have a deeper look in one of these techniques, because driving or having like these advanced local path planners, you can choose from a wide variety. We just heard a few minutes ago, there's like optimization techniques, for example, the MPC, which samples a trajectory, which is like a control technique, but it samples a new trajectory, and that one we can follow, and that's like a big optimization problem. The optimization requires a convex problem description because non-convex problems are like very hard to solve. Optimization is like computationally expensive. You need like good solvers, you need a good optimization problem, good constraints, you need to know a lot about your model. And in the end, we get a very good smooth path with no discretization issues. So like we have some trade-offs, advantages and disadvantages. Then number two, in the middle, there's the one-layer graph search. And what you can think about that is like you see the car, and from the car, we are sampling trajectories into the future. The thing with this is it's like very robust, it's very fast. You can sample a lot of trajectories into the future. You can vary the cost functions. You can even go with like high horizons and optimize that. And that's like very robust, but you cannot do like very complex maneuvers. And therefore, we're coming into the last part, which is called the N-layer graph search. And what happens here is that we create a graph. And a graph consists of edges and nodes. What we do, we connect all these edges and nodes together, create that for our complete racetrack, and then drive exactly on this graph. So the optimal, or what we have here, the possibilities is that we can drive complex maneuvers and we can pre-compute parts. So that's like a very cool trick we can apply to the racetrack because we go on the racetrack, we train on the racetrack, we have a lot of knowledge about the racetrack beforehand, and that's why we can choose that. And that technique, I want to show you today a little bit more in detail. So what we are doing to apply this graph-based trajectory planner, the first thing, we get information about our racetrack. So we need the inner bounds, we need the outer bounds, we need like X and Y position to create the racetrack, what you see on the left side. And what we then do with this racetrack, we create a graph on this racetrack. A graph consists of edges and nodes. And the first thing we want to do here is we create a state lattice. So we split the track into lattices. And the cool thing here is we can make these lattices wider, we can make these lattices closer. And now you can imagine the wider we make the lattices, the more space between the lattices is and the more space the car has to select. But if that's like so wide between the lattice, we might not get the best vehicle behavior. So we make it very, very closely. Then we have like a very good vehicle behavior in the end, but our search is increasing when we search on this graph. So you see the discretization starts here at exactly that point when we define the lattice. The second discretization we integrate here is the so-called nodes. On each of these lattices, we put now a node. We can make this also wider, like only 2 nodes on one lattice, or we can, what you see here, like 10 nodes on one lattice. What we then do in the next step, we calculate the splines and we connect each of the nodes with each other. And what you see now here in blue is our graph network. That's like a complete graph that is capturing the whole racetrack. And this graph consists of splines. And just so everybody knows, a spline, that is like a piecewise polynomial. And it's like a curve, what you see here on the right, that is broken into consecutive segments, each of which is a low-degree polynomial interpolating the control points. And what we have in splines is like 3 versions of the continuity. The first one is called Z0 continuity, which is like continuous only in position. Then we have C1 continuity in the middle, is like continuous in position and tangent line, which means position and speed of the car. And then we have C0, Z1, and Z2 continuity, which is like continuous in position, tangent line, and curvature, which means for our car, position, velocity, and acceleration. That means if we have the transition from one spline to the next, we can guarantee that our graph is continuous from position, speed, and acceleration. And that's what we're doing here. So when we connect now our graph with on this racetrack, what you see here in orange is one example, like from one node to possible the next nodes. The first thing you see here is that we cannot drive from one node to all of the other nodes. That is basically a very, very simple explanation, because our car can only drive some certain maneuvers. So if you are like on a certain speed, if you are in a certain position, your car cannot move, for example, to the left outer bound of the racetrack. It's not possible from a dynamics point of view. So first of all, only a handful of nodes are connected to one node. And then this slide here is the most important one. We, as an engineer, we define a so-called cost value for these nodes. And this is basically where the magic happens of this graph planner, because in this cost values, we define how many costs does it cost for the car to drive on this spline. So what you see here is like a cost function we defined, which says, please stay close to the race line. The farther away you're from the race line, the higher the costs are. Or what we also integrated is the average curvature driven on this spline. If our spline, for example, has like a high curvature, we say this is a high cost for the car to drive on, and that's nothing we want to follow. Because we want to always drive the minimum curvature, we want to drive low curvatures, we want to drive less steering and more velocity. And you as an engineer, you can define whatever cost you can think of. And you can vary the parameters here, and you will see that your car has then a completely different behavior. So we define now the cost values, and everything you have seen now can be done offline. And that's very cool, because now we have done all these computationally expensive things. We save our graph, and then we move online to the car. So you go onto the car, you bring your saved, you bring your USB stick, put it in the car, download this graph network, and then start the online part. And the online part you can think of as a calculation that runs every 20 Hertz through the complete pipeline you see here on the right, which means our car is starting on the racetrack, seeing now the complete graph. The first thing the car does is fetching the updates, like where am I on the track? What is happening around me on the track? For example, objects that are driving around, where those objects coming from, like from an object detection or from V2X, we don't care right now. And the first thing we do in the online part is we setting up a so-called local node template by filtering edges of the full graph. First of all, based on a planning horizon, is what you see here. We only look into the future for around 200 meters, and the rest we don't care about. Because if we look into the future far more, then our search is getting more computationally expensive. And the second thing we are doing here is we are creating a so-called set action template. First of all, we want to drive straight, then we overtake on the left and overtake on the right. And therefore, we're just searching in one of those three areas. And therefore, we can also decrease the computationally expensive search for a right trajectory. When you have found such an action template, we then need to integrate the opponent prediction. This is also a very, very important part, because with the opponent prediction, we get rid of edges and nodes that are in the future of the opponent car. So you can think of that this is an area our car does not want to drive in, which means the better your prediction of the opponent's behavior is, the better is the path planning in the end. You can do that with like a database approach or an LSTM approach, or even like an online learning and adaptation approach. Whatever prediction you can think of, you can also say like, oh, the next 10 meters in front of the opponent car, it's like a no-go zone for me. You can also do that. That's like, of course, not the best approach, but you could do that and then say, I don't want to drive there. So now you have all the data gathered of your opponents, and now we start to create our trajectory. And what we do with that is we search for the shortest path. And now you can remember why I introduced the costs, because now in this blue area, we are searching for the sum of all the splines that have the lowest cost. Now you can see what that makes. If we have like a complete different cost function, this creates a complete different behavior of the car in the end. And when we found this trajectory, we then re-optimize or recalculate the curvature to have this continuous spline in Z1, Z0, and Z2 continuity, because what we want to have is like a continuous behavior of the car in all states, like from acceleration, velocity, and position. So our car drives smooth around this trajectory. And that what you see here in black on the left side, after doing all these processes, this is from the perspective of the graph planner for this time step and this opponents and this prediction horizon and this horizon we look into the future, the best optimal trajectory we can follow. And therefore we can have a very dynamic car behavior. The final part now is a velocity profile calculation. In our case, we can do that with an introduced forward-backward solver or with even a bigger optimization problem that integrates energy strategy, the friction estimation, and the friction potential. So you can optimize for that. And then you have like the path and the velocity profile that gives you the right vehicle behavior in exactly that time step. And that's now creating the local trajectory for this time step, which integrates the curvilinear distance around the racetrack, the coordinates X and Y, the heading of the car, the curvature, the velocity, and the longitudinal acceleration. So in this trajectory is now everything integrated that you need for finally controlling the car. Because now we only created the trajectory, but have not controlled the car at all. Here's a short video that shows you this graph planner in action. And what you see on the left side is the trajectory planner that's planning this graph with the techniques I just introduced to you. And on the right side, you see that applied to a real car. So on the left and right side, you see exactly the same behavior, once in simulation and once in the right side. And what you can see here is that we are trying to overtake an opponent and we are replanning the path every time. And now what you see here on straight, it figured out that there is like enough space to overtake an opponent. The car is driving on the right side, the opponent staying on the left side, and we are finishing the overtaking maneuver. So that's basically the output of the trajectory planner. Now it's time for us to control this trajectory. And that's something Madhur just introduced, for example, the pure pursuit controller. When we have the raceline created or the trajectory generated, we need to control exactly that trajectory. And we have like a wide variety of techniques. Pure pursuit was just introduced. We have the Stanley controller, we have the linear quadratic regulator, or the model predictive control. Whatever you choose from, you can apply this trajectory planner or combine it with whatever controller you can think of. All of them work. One of them work better, some of them work worse. Of course, model predictive control is something which is like, yeah, gives you a lot of advantages. And therefore you can control this trajectory. I'm in the end of this short presentation about the graph-based planner. You can access all the code I just introduced you here on our GitHub repository. I created a YouTube video for you that explains the code in detail and shows you how to apply this graph-based planner. And therefore, I'm at the end of this presentation. And if you have any questions, you can ask them in the chat. Thank you very much for listening. Okay, I see. So we have one question about the controller. LQR requires a linear dynamical system. Racing dynamics are not linear. So you might try to do sequential linearization or some trick like that. So yeah, the question is,
sorry, Johannes, this is Houssam. So this was my answer to a previous question that was asking, oh, can I just use LQR?
Okay.
Yeah.
No worries. All right, great. Then we have like one question directly for me. Is there such a thing as control-based cognition when it comes to path and raceline planning? Okay. So this question is mostly pointing towards the creation of the race line, which special behavior of the car. And the short answer is yes, we can do that. The long answer is there are like a few papers out there that focus on race line trajectory generation with special vehicles, for example, rally vehicle. So what the rally driver is normally doing, or what you sometimes see the rally driver, that he is driving into the corner, is flipping the car and drifting into the turn. These kind of maneuvers you can apply with your control techniques and use in the optimization problem for both the optimal race line generation or even the local trajectory generation. Of course, this is like very heavily control based and is not applicable for normal race cars. So what I showed to you today is the racetrack on asphalt, Formula One cars or Formula cars or go-kart styles. That's what I introduced you to you today. And basically that's where you have the fastest vehicle behavior around the track, because that's what you want to achieve. Okay, I think I answered the question. Maybe I can put some papers in to show to you where the people apply that into the rally driving. Another question is vehicle dynamics considered for the optimal planning? The third one, yes. So the minimum time problem I explained to you is a so-called optimal control problem, and this optimal control problem is using a so-called double track model. So you can think of that we have like kinematic model, then we have a single track model, and then we have a double track model. And with each of the models, we are increasing the number of parameters we need, but at the same time, we are increasing the model accuracy. For example, the kinematic steering does not consider any lateral dynamics. The double track model considers all of them, but even like the pitching of the car, which means if you brake with a car, your car makes this movement to the front, which means it applies more forces on the tire to the front. That kind of behavior is exactly modeled in this optimization technique. Again, it requires a lot of parameters, but therefore you can capture the real vehicle dynamics behavior. One small point is like very important here. It's the friction coefficient. Even for our global optimal race line optimization, even if you capture the dynamics very well, the friction coefficient is something you don't know beforehand and you only can estimate or assume. If you're driving, for example, on a wet surface, your global optimal trajectory would change completely. Okay, and the last question I think I would answer, and then we move on to some, is can you speak more about on the costs that are chosen to be applied to the graph edges? Clearly, this is not the length of the edge, but what is the cost of any particular edge? So the cost value is something you can design on your own. In our case, what we say, if you're driving on, for example, this trajectory, and this is the race line, we take, for example, the difference to this cost, we take the difference to this spline, which means the higher the distance to the race line, for example, the higher the cost of this trajectory here on the right side. The second thing, for example, which we designed is the curvature you're driving exactly on the spline. So think about, you have like this high curvature, which means in average on the length of this trajectory or of the spline, you have like high steering. And that's something we do not want to have, okay? So what we say then, if you have like a high curvature on the spline, we give you a high cost value here. And then we have like a couple of more cost values. I don't want to go into detail here, but just to give you an impression, what you can think of. And more or less, we need to capture the vehicle dynamics and the vehicle behavior efficiently with this kind of costs. Okay, the last question, computational complexity. This,
Johannes, perhaps 1 minute.
Yeah. The last question is computational complexity. So this graph planner runs with like 20 to 25 hertz on your computer, which is like very, very fast because you can do the overtake maneuvers. All right, I hand over to Houssam. Thank you very much for listening. And yeah, thanks for being here.
Thank you,
Thank you for the great
Johannes.
session.
Yeah, actually, that last answer provoked a question that I have, but I'll ask it offline. So I'm not going to actually talk much. I'm quickly going to hand it over to Khushal Brahmbhatt, who's a master's student graduating this year from Oregon State University from the robotics program. Khushal, go ahead.
Yeah. Hey, everyone. You made it. The final talk of this workshop. All right. So let me just share my screen. All right. So my colleagues have been talking about the pure pursuit and raceline optimization, how to race an autonomous vehicle. I'm going to be talking about multi-vehicle racing. When you're racing in a team and you have to handle collision-free paths between the vehicles in your own team, how would you go about deconflicting these paths in an efficient manner? So a little about me. I'm a graduate student at Oregon State University. I'm doing a concurrent master's in robotics and artificial intelligence. My work is largely deals with motion prediction and planning in autonomous vehicles and unmanned aerial vehicles. I've previously worked a lot with deep learning methods and reinforcement learning and multi-agent path planning. Currently, my work studies the application of fairness in motion planning. When you have a multi-agent system, how would you plan for fair paths in such a system? And we use formal methods, specifically temporal logics, to study this. And temporal logic is a way of representing knowledge using formulas, and we use this to define our missions, and we use optimization-based methods for motion planning. I work with Dr. Houssam Abbas. He studies the use of formal methods for verification, motion planning, and making ethical decisions in self-driving cars and drones. So yes, so we've been talking throughout this workshop on how you would go about optimizing the trajectories of your vehicle while racing, or how optimizing a race line. But if you're racing as a team, how could you efficiently deconflict conflicting parts of the vehicles in an efficient manner? And we look at a way of doing this by assigning priorities to the vehicles on the team. So you could assign static priorities where you begin with each vehicle is assigned a fixed priority, and the vehicle with the higher priority always gets the right of way to its optimal, to continue on its optimal racing line. Or you could assign dynamic priorities where the vehicle that is in the lead, the leader, gets the right of way, so it doesn't obstruct or it doesn't slow down. It's not slowed down by other vehicles on the same team trying to get on its path. And the good thing is about this, as we won't be looking at how we assign these priorities, but we'll be looking at an algorithm that we can use to leverage these priorities to achieve deconflicting, or to deconflict the parts for the optimal parts for these vehicles. So a little bit of an overview of the motion planning paradigm. I think it's already been talked about in one of the previous talks here, but I'll just go over it really briefly. So in the motion planning pipeline, we have the mission planner, which is the high-level planner that given point A, you want to start from point A, go to point B on a map, and find the optimal, you find the optimal route to do this. The behavior planner finds driving actions and maneuvers that allow you to safely achieve the plan generated by the mission planner. And then you have the local planner, which will use the dynamics of the vehicle to achieve low-level control and to achieve the desired trajectories of these vehicles. So the work we're doing falls in the behavior planner, because we're studying how we would dynamically find the actions or maneuvers to take instead of in case of obstacles or deconflicting parts between vehicles. So our focus here is on using an algorithm, using a decentralized algorithm where you have limited communication between the vehicles, and we're focusing on how to leverage priorities for like a reward function for a learning algorithm. So in the related works, there's been a few approaches for achieving multi-agent path deconfliction. There have been heuristic-based methods where the optimal path is known beforehand. As we're looking here, we're assuming we already have an optimal racing line, as Dr. Betz talked about. And other works have looked at assigning static priorities based on things like the environment or the environment complexity or the capabilities of the robots. Another class of methods for multi-agent path deconfliction looks at searching, so either searching through a tree or some using centralized solutions such as mixed integer solution optimization methods. The problem with this is they're very expensive. Their runtime is variable, and they're not suitable for real-time control where you want to make decisions instantly in real time when you're racing. So some background we will need to know before I talk about our algorithm is reinforcement learning. So reinforcement learning is a way of learning by interacting with the environment. You have an agent in a particular state, and the agent takes some action through either exploration or exploitation of some optimal policy. And based on the action it takes, it will receive a reward, either positive reward or negative reward. And this reward is used to reinforce how good or bad the state or the action that it took was from a particular state. So it's essentially a way of learning by when you don't have training data. So a way of learning by interacting with the environment and using the rewards you get to reinforce your optimal policy. Another way of finding a default policy, finding an optimal policy is Monte Carlo tree search. So in Monte Carlo tree search, it's basically a tree search algorithm where you start with some root node, and there's a selection phase where you will find optimal nodes, optimal child nodes, and you will go down the tree by selecting the optimal nodes. And then there's expansion phase when you reach leaf node, what action you should take to explore more of the action space and to expand more of the tree. And this is done up to the selection expansion phase. The selection phase is done up to a given search depth. And once you reach there and you expand to some node, and then you run a simulation where you continue running this the default policy of the selection of just expanding the tree from there. And at the end, you have some reward that when the game is finished, and you can backpropagate the reward to assign values to the rest of the nodes in the tree. So the algorithm we look at here is called neural tree expansion. It was published in the paper here, Neural Tree Expansion for Multi-Robot Planning in Non-Cooperative Environments. And what they basically do is they combine the idea of Monte Carlo tree search and reinforcement learning to find a more efficient way of searching through this tree. So I will walk us through the neural tree expansion algorithm. So what makes it particularly suitable for using in real-time systems is that the offline training loop is decoupled from the online decentralized deployment phase. So in the offline training loop, we can use self-paced samples and exploit demonstration data to train our neural networks, which are used to bias the tree growth. And the policies that you learn in the training loop, we can use them in the deployment phase with the minimum computation power. So at the core of the algorithm, the learner is the Monte Carlo tree search, and the learner generates self-placed samples. So we could start with some random scenarios where you place agents at some starting positions, give them goal positions, and we use the Monte Carlo, whatever the untrained policy for the Monte Carlo tree is to just search through this, and this is fed to the experts. So once we reach the expansion, we've taken the selection expansion phase to some particular search depth. And then we will select some action to take using an exploitation policy. And we will get a reward for this action that we take. And this reward can be used to train, to update the values of the states, or to update the policy and value networks, which are neural networks. So the expert is essentially using a reward function, which I'll get into in a bit, to generate demonstration data or training data to train the policy and value networks. So the policy and value networks are essentially just neural networks. So the demonstration data is used as training data to train our neural networks here. And then these networks are used to bias the tree growth for the Monte Carlo tree search. So the Monte Carlo tree search uses the value network, just another neural network, in the selection phase. So how does it decide which node to select in the next at the next level? And it will use the value neural network to select optimal nodes. And when it reaches the expansion phase, when it has to decide which node to expand, when it reaches a leaf node, it'll use the policy neural network. And so this is an iterative training process where the Monte Carlo tree search algorithm keeps getting better and better using the policy and value networks, and it keeps generating better training samples, self-play samples, which are used by the experts as better training data, and it continually keeps iterating, updating the policy and value neural networks. So the policy and value neural networks, they're used to bias the tree growth for the Monte Carlo tree search. And the neural tree expansion algorithm is basically just an efficient way of training Monte Carlo tree search. So what we're focusing on here, our contribution to this work was how do we assign the rewards, or how do we leverage priorities to learn a reward function, to design a reward function that can be used in this algorithm to achieve path deconfliction. So I will talk about our state representation for this problem. We have an agent, the agent or the vehicle at the ego vehicle at the center, and it has a limited sensing radius given by the circle around it, and it can only, there is limited communication between the ego vehicle and other vehicles on the team, and so we segment the space around the vehicle into 8 segments. And if there is any, it can communicate with any vehicle that is within this sensing radius. And for each segment, it will be affected only by the priorities. It will only be affected by the priorities for the vehicle that's closest to it in each segment. And these are denoted by the green circles within this segment. So to talk about our reward function. So we designed a reward function where we could leverage the priorities for each agents. And there's basically 2 terms in this reward function. The first term is the distance to the racing line, to the optimal racing line. So when you take an action, you will receive a reward. So if the action you take takes you closer to the optimal racing line, you will receive a positive reward, a higher reward. If you take an action that leads you further away from the racing line, it will give you a lower reward. And this is given by the first term, the 1 by D, 1 by dg. And the second term is how we use the priorities to design for our reward function. So when there's another vehicle that's closer to the ego vehicle, this is factored in by the 1 minus dxi by rx. So this is measuring how close you are to another vehicle. And the idea behind this is that the closer another vehicle is to you, the higher your optimal path is going to be affected. If the vehicle is further away from you, then you should just focus on, you shouldn't worry about deconflicting paths. You should just focus on just continuing along your optimal path. That's the one by DG term. And the PX is the priority for the eco vehicle, and PI is the priorities for the surrounding vehicles. So the idea of using this is agents with lower priorities will get negative rewards if they're next to a higher priority vehicle. And so this essentially discourages lower priority vehicles from getting close to higher priority vehicles. And it allows high priority vehicles to get the right of way when vehicles come close to each other. So our reward function is basically two terms here. We're looking at the first term, that's how close you are to your optimal racing line. That's one of the objective functions. And the other objective function is how the priorities will affect your reward function here. So a base case that we selected for our experiment is just assuming you have two agents at two corners and they have goals on the opposite diagonals. So we're assuming that the optimal path here for them is just a straight line diagonals, and it guarantees a collision path at the center. So the reason we selected this simple base case was that it would guarantee some conflicting behavior at the center there. It would allow us to observe how the algorithm affects the behavior of these vehicles when if they have a conflicting path between them. So this is currently a work in progress, and at the time the results were collected, we had done 10 out of 50 iterations. However, each iteration, we're running 100 epochs. In each epoch, we're running 100 iterations. And in each iteration, again, these are for the expert demonstrations. For each iteration during training, we're searching down to a search depth of 25. So the outer loop of each training iteration is actually quite expensive. The training process is essentially just how we train neural networks. And so this is one of the results we observed when using the priority reward function. The agent in blue is the higher priority agent, and the agent in red is the low priority agent. So you will observe that when the agents get close to each other, the red agent stops in its path and gives way to the blue agent to continue. And once it has moved forward, it will continue along with its path. However, there is some interesting behavior you'll observe here, which comes as across as a limitation of our reward function, which I will be talking about. And this is the result we observed when we didn't use priority rewards. However, this is a little confusing we weren't able to observe the conflicting behavior. It seems our algorithm didn't learn even the optimal path or the optimal path well enough. And there was no point of conflict for us to even be able to observe the behavior of the reward function. So yeah, I talked about one of the limitations for our reward function, as you will, so in the result here, you can observe when the red and blue agents get close to each other, the red agent does give way to the blue agent, but you can see the blue agent coming back, circling back to the red agent. So it seems like the agent with the lower priority is being discouraged from getting close to the high priority agent as a result of the PX minus PI term here. But the agent with a higher priority agent, if X is a higher priority than the agent I, this reward is actually a positive number, and it's kind of encouraging the higher priority agent to not only to go to its optimal racing line, but to also chase the lower priority agent. So this is a limitation of this reward function, and what we could do here is assign weightage to these terms. Right now, these two terms are unweighted, but we could assign weightage to these terms, the two terms here, based on the priorities, so such that the higher priority agents are focusing only on their distance to the racing line and not looking at the low priority agents. But if you're a low priority agent, you do want to stay away from the high priority agent and give it weight to continue to on its optimal path. We did not implement obstacle avoidance in our experiments yet, but an interesting idea is that we could use the same reward function for obstacle avoidance by assuming that the obstacles are agents, and we give these agents the highest priorities or infinite priorities, which always discourages all the agents, the rest of the agents, from going near the obstacle. We right now we also use discrete state action space where there's 8 segments. There's only like 8 actions the agent can take in the 8 angles around it. We could use a continuous state action space, and we could also use the vehicle dynamics to generate a trajectory that's more in line with what we expect to see with autonomous driving. And we could also use some low-level control algorithm or planning algorithm like a lattice planner to get better, more suitable trajectories for autonomous driving. So if you would like to reach out to me, if you're interested in these areas, for multi-agent systems and motion planning, you can reach out to me on my email or LinkedIn. And that's my talk today. Thank you. I'm open to take any questions. So I see a question in chat. Are there successful end-to-end trajectory papers, deep learning or reinforcement in the field of racing that have been successful? Yeah, there is a lot of deep learning end-to-end is quite a wide area. There's a lot of papers in that area. I feel like the issue with deep learning is you need a lot of training data to train your models in, and you need to be looking at a lot of edge cases. If you miss out on an edge case, for deep learning, you need a lot of training data. It's the same, what we look here with reinforcement learning is that we're generating training data on the fly using the Monte Carlo tree search. So they're both useful algorithms. I don't have any paper off the top of my head I can mention for deep learning for trajectory planning, but there's definitely
Khushal,
there. Yeah.
Khushal, I can address that in the summary session that
okay.
will follow.
Yeah, perfect.
So are there any other questions for Khushal, or we'll go into a summarization session to be able to bring today's event to a close? First thing I have to say is give a round of applause to yourself. You survived this marathon session. Let me use the next maybe 10 minutes or so to quickly summarize some of the topics that we covered today, and as well as provide some directions for future interactions. Today's session was intended to be a bird's eye view of all the different things that are possible with the F110 platform, and all the different directions in which this can lead us out into. But even as we've sort of gone through this process, we've highlighted the fact that there's a lot of information that is on the f110.org website. And I'll take the next few slides to kind of walk through that, just to give you a little picture of what you can expect to find, and then leave you to your explorations. But I wanted to take this opportunity to thank all the speakers. They took valuable time out of their schedule to give us this overview. And so let me start the applause. Thank you. In terms of what we're attempting to do with respect to the community, that started in 2016, as Rahul and Madhur pointed out, and has now grown to a stage that you're seeing today, is that, can you see my screen? Can everybody see? Okay. Is that the platform itself has undergone a number of changes over the years. So what started out as a initial mechatronic realization has since then, there have been improved LiDARs, improved power control, improved cameras, improved computation, and so on. And so for people who are looking into this, there are opportunities there for building the next generation of the F-110 car. But I think for a lot of people, having a platform, a reference design and a reference platform, and being able to build out on it, in terms of focusing on the algorithms, the ROS-based architecture now allows easy access, relatively easy access to this platform, and then allows the research that you're seeing in terms of safe autonomy, secure autonomy, coordinated autonomy, and efficient autonomy. And you saw samplers of all of this in terms of the research that was enabled. On the f110.org website, what you will get is an opportunity to be able to do this for yourself. So the mantra of the F110 is build, code, and most importantly, the most fun part, race. And so what I've done in the next few slides is taken some snapshots of what you see on the website. So in terms of the build documentation, the entire bill of materials for the vehicle is available. We were also fortunate that this was proposed as an NSF CCRI proposal, which was funded, and this was intended to help create and develop this community of people interested in these F-110 scaled vehicles as an enabler for both education and research. And so in the context of education, one of the challenges that we kept hearing from people was this idea that, it would be nice if you had a curriculum and a set of options. And so there were multiple iterations of this, of the curriculum that were developed. Some of it is on this website. Johannes, over the past year, has actually developed an open edX course. And after I'm done, maybe I'll ask him to maybe walk you through what the open edX course looks like on the website. So maybe he can get ready for that. But also we had this opportunity to use racing for all the reasons that everybody has motivated to help push the frontiers, to basically scaffold, as Rahul and Madhur mentioned, some of the early races were using only reactive planning. But as the platforms and the experience with these platforms got better and better, there was more of an opportunity to infuse that research back into the education part of it. And so this is the part that Rahul highlighted, where there is an entire course that has been deployed in course material that you're seeing here that will enable people to jump into this process. Different groups have deployed this at different levels. So for example, if we are an automotive engineering department, we may tend to focus more on some of the mechanics, some of those types of aspects. Other groups have focused on other aspects as this has gone on, and there are the curriculum that has been developed is modular and it's customizable, and you can now use it to deploy as many or as few of these modules. The intent was also that it wasn't just a course to be taught in a classroom setting, but there's an opportunity to do this in a flipped classroom setting. And in particular, for clubs to be able to take advantage of this and set it up as modular courses that they would pursue, as a modular deployment that they would pursue. So in response to that mandate, there are a number of the people that you see here have actually developed entire YouTube lectures, primarily to support their own courses, but now made it available for everybody to be able to access it through just the open web. Over the years, this is an old slide. And so this was, I think there's probably double this number of universities that have now taken some sections of this and started to deploy this in their various undergraduate, senior level courses, graduate courses, and so on. But what you're seeing and what you would have heard frequently in this tutorial is that the platform and the context now enables people to look at research that was in the intersection of formal methods, control systems, and machine learning. But as the needs grew, you could start to see sensing and perception, and better sensing and perception, better planning, the ability to now use high performance compute in the form of the GPU hardware accelerators, and the real-time mandate for a vehicle such as this operating in a race setting, opened up more horizons. And in this context, being able to now view this in a system context and be able to say, how do changes in terms of GPUs ultimately affect agile autonomy? Or how do changes in some small module affect the whole? It gives us a platform to be able to evaluate things of that nature. And so the mechatronics and power systems part of it is still, it's starting to grow. But if there are people who are interested in this, please contact any one of us, and we'd be happy to find ways in which we can create the next generation of the F-110th car. So just highlights of some of the types of research that it started to enable. You saw this discussion of follow the gap, model predictive control, the notion of an end-to-end neural network learning, for example. In many cases, the courses ended up using some of these as final projects in their courses. And over the years, it's gotten better and better. So these are examples of some of the final projects at Penn that were deployed in the context of these different research areas. And so some more examples of this. So for lane keeping assist, for groups that were only interested in perhaps a computer vision context, but now it had to be further researched in the context of an entire system. The simulator aspect was something that we talked about, where the ability to test algorithms in simulation and then be able to deploy in a real-time context on an actual physical system will prove to be very useful. I think Madhur talked about it, Johannes talked about it. And in these cases, I think sometimes necessity caused by the pandemic actually accelerated the need for the simulation dimension. So Docker-based implementations, the AI gyms, et cetera, were really pushed. further along in their development during the time when everybody had to go virtual. I believe Johannes was responsible for some of these aspects too. Now, to the question that somebody asked about, how can I take advantage of something like this and find out more about this? If you were to navigate to the research page on the F110th website, there are links to different kinds of theses, papers, code that pertain to different research projects that people have now deployed using the F110th platform. So this is an ever-growing collection. And so you have both, you've got research articles, you've got theses and projects, and you also have how the different places where the F110th has been reported in the news. And finally, the international competitions. So over the years, the F110th has proven to be a very fun opportunity to bring people together, typically at international conferences. And so what you're seeing here are the different places at which the F110th program has run competitions. So things sort of came to an abrupt halt for the physical competition piece, at least after 2020. But we had virtual competitions after that. And now, most critically, I wanted to use this opportunity to advertise an upcoming competition. So maybe I'll ask Johannes to unmute and tell us a little bit more about this, because he's been the prime on setting up this competition.
Yeah, thank you very much, Venkat. I think that's a good point. So everything you just saw, all the codes, all the theory is just theory. And we want you and everybody from all over the world come and visit us in Philadelphia, in the USA, and be part of our 10th F110's Autonomous Grand Prix competition. That means you can buy a car or build a car on your own, travel to Philadelphia, write the code, and then race with autonomous racing enthusiasts from all over the world. We currently have already 25 participants that come and race in Philadelphia. We also, for the people who cannot travel and are not able to come to the US, probably for some COVID reasons, provide this year a special virtual competition, which means you can just write your code and upload it to our server and then race against others from all around the world. And yeah, we try to bring everybody together here in Philadelphia, all the people that are interested in this field. You can come and bring your car or race virtually. It's up to you, but we will love to see as many participants as possible.
Right. And the thing that I want to highlight is for people who are not sure what ICRA is. ICRA is the International Conference on Robotics and Automation. It is the flagship conference of the IEEE Robotics and Automation Society. And over the past few years at IROS, which is Intelligent Robot and Systems, and at ICRA, the F110th group has been developing both competitions. So the IROS competition ended up being virtual. The ICRA competition is now a mixture of both virtual and physical. But in addition, and this is also you, Johannes.
Yeah, in addition, we will have a workshop. So today you listen to us as a small group of people that wrote some code, but the autonomous racing community is much bigger. It's an international community of people that dedicated themselves and their research work to the field of edge case, edge autonomous driving and autonomous racing. We have, for example, Brahmbhatt, the former CEO of RoboRace. We have Marco Betonga, Sergio Savarese, and Alexander Wisniewski, the three team leaders of the leading teams from the Indie Autonomous Challenge. Mauro Salazar, who's telling us some optimization techniques for combining energy management and path planning for race cars. Evangelos Teodorou from Georgia Tech, and Mike Schwager and Jonathan Go will show us their research and work in the field of path planning and interaction of vehicles. And especially Jonathan Go, he's from Toyota Research Institute, which shows us that autonomous racing is not only something in the research and university field. Toyota Research Institute is showing us how to enable drifting of autonomous cars to enable safe maneuvers. And finally, Srikant Sipali from Texas A&M University and Peter Werman. And Peter Werman is the last participant here, and he is from Sony AI, and that team of Peter showed how to optimize and create a reinforcement-based autonomous race car in Gran Turismo. And that technology is available to all the Gran Turismo users. So we have like, personally for myself, that's like an awesome field of speakers we have gathered here together only for one topic, autonomous racing.
So with that, I think I've come to the end of my presentation. I wanted to use this as an opportunity again to thank all the speakers and open it up to any final questions that people might have, assuming that you're still on the call. I see 31 participants, so that's a good sign.
Yeah, I see people asking about collaborations over the ocean. Of course, the community is big. We have like our emails are available. The F110's website is available. And if you reach out to this kind of group, then you reach all of us. So yeah, just reach out.
So I'll give it a couple of minutes longer in case people have questions and to put in that furiously typing it into the question and answer. I don't know if there's a way I can open up the mic in a webinar.
I'm not sure, but I saw some questions. I just answered. So is the competition made just a competition, or will we be able to collaborate with people at Penn to develop our code? So it's mainly a competition, but what you do there is you engage and network with fellow researchers in the same field. Currently, you can subscribe to the competition and say that you want to join a team, and then we can connect you to other teams. So you can collaborate there, but it's mainly that you come, take part in the competition and network with all the enthusiasts in this field. A second question was, is it possible to run MPC in F110s? Yes, we have some researchers that applied the MPC to the F110s car. The computation on the current F110s vehicles is enough to run an MPC, but it depends on your problem formulation and the solvers that you're using, but the car is able to run the MPC.
Yeah, and the additional thing I'll say is, I think with the old cars, with the TX1, it was able to do it. With the TX2, it was certainly able to do it. And I think with some of the newer platforms, you have the ability to now swap an existing platform for something of your choice. I think we had the design was optimized to keep the costs somewhat lower, but with the rest of the framework largely remaining the same, you can now use Xavier or any other suitable platform. Some people have used mini ITX type platforms and so on. All right, so I think we had originally planned this for a 4-hour session, but I think it is a Friday. It is spring break for some of us. here at Clemson at least. And so we'd want to thank the speakers once again. And as I said, the email addresses are available, and we'll send everyone an email once the videos become available from this session. Thank you again for. There's a last. There are a couple of questions, I guess.
Oh, it's the platform. Okay. If it's limited to LiDAR or cameras being used. No, we use LiDARs and cameras, but if you have different sensors, you can put them on the car.
Yeah, at this point in time, I think like Rahul motivated, right? Tesla is using an all camera solution. And so using that framework, it makes sense to not use a LiDAR. And in other contexts, people are looking at mixed LiDAR and camera solutions, efforts at sensor fusion, things of that now become possible. I'm not sure, Johannes, you may know better if somebody's already doing some of the, I think for some of the semantic segmentation efforts, people are using the cameras to now assist in labeling the LiDAR detected obstacles.
Yeah, that's what they do.
Yeah. All right. So thank you one and all for staying with us till the very end. And have a good rest of the day and the weekend. Bye now.